Hey everyone, welcome back to Scientific Discovery Hub. Ever wondered if the universe could send us a message from its distant past? What if a visitor from another corner of the galaxy arrived at our doorstep, carrying secrets older than Earth itself? Well, get ready to embark on a mind-bending journey, because today, we are diving into the story of 3I Atlas, a cosmic time capsule that might hold the key to unlocking 7 billion years of galactic history. Discovered in July 2025, 3I Atlas is the third confirmed interstellar object to zip through our solar system, following the mysterious Oumuamua and 2I Borisov. But here's what makes this comet extraordinary. It's not just a random visitor. Scientists believe it originates from the Milky Way's thick disk, a primordial region filled with ancient stars. If true, 3I Atlas could be over 7 billion years old, twice the age of our planet, and a relic from when the galaxy was in its chaotic infancy. In this video, we'll explore how this icy traveler became a time machine, offering a rare glimpse into the conditions of the early universe. We'll break down its hyperbolic trajectory, its zooming through space at 58 kilometers SOS, decode its strange chemistry, including cyanide and carbon monoxide, and explain how cutting-edge telescopes tracked its faint glow across the cosmos. Along the way, we'll uncover what 3I Atlas reveals about the formation of planetary systems, the evolution of the Milky Way, and even the potential for life's building blocks to drift between stars. Could studying this comet change our understanding of where we come from and where the universe is headed? Stick around as we unravel the science behind this cosmic enigma, from its explosive cometary activity to its eternal farewell flight out of our solar system. And if you are as fascinated by interstellar mysteries as we are, don't forget to like, subscribe, and hit that bell icon for more mind-expanding content. Let's dive into the story of 3I Atlas, the oldest comet ever observed, and discover how it connects us to the vast ancient tapestry of the cosmos. Imagine a solitary traveler, born in the shadowy depths of a galaxy far older than our own, now drifting silently through the vastness of space toward our corner of the cosmos. This is 3I Atlas, an interstellar comet that has transcended the boundaries of its home system. Discovered in the summer of 2025, this enigmatic object is no mere transient. It is a time capsule, a fragment of the Milky Way's ancient past. Its journey spans billions of years, and its arrival offers humanity a rare opportunity to study material that predates the formation of planets, stars, and even the sun itself. As it glides through the inner solar system on a hyperbolic path, 3I Atlas carries with it the chemical fingerprints of a primordial era, a time when the galaxy was young, turbulent, and teeming with the building blocks of life. To observe this comet is to gaze backward in time, to touch the remnants of a cosmic epoch that shaped the very fabric of existence. What stories does 3I Atlas whisper to us? What secrets does its icy heart conceal? 3I Atlas, formerly designated C2025N1, Atlas, is the third confirmed interstellar object to traverse our solar system, joining the ranks of the mysterious 1I Oumuamua and 2I Borisov. Discovered on 1 July 2025 by the Asteroid Terrestrial Impact Last Alert System, Atlas, at Rio Hurtado, Chile. The comet was initially a faint smudge in the night sky, its light barely perceptible to the instruments tracking it. At the time of discovery, it was 4.5 astronomical units, AU, from the Sun, hurtling inward at a blistering velocity of 58 kilometers per second, over twice the escape speed of the solar system. This extreme speed, combined with its hyperbolic trajectory, confirmed that 3I Atlas is not bound to the Sun and will eventually exit our cosmic neighborhood, returning to the interstellar void. What sets 3I Atlas apart from ordinary comets is its origin. While most comets in our solar system originate from the Kuiper Belt or the distant Oort cloud, 3I Atlas traces its path to the Milky Way's thick disk, a region populated by ancient stars and remnants of the galaxy's earliest epochs. This distinction places it among the most ancient objects ever observed, with estimates suggesting it could be between 7 and 14 billion years old, far older than the 4.6 billion-year-old solar system. Its nucleus, though shrouded by a coma of gas and dust, is believed to measure less than 1 kilometer in diameter. Yet within this tiny world lies a volatile cocktail of carbon dioxide, water ice, carbon monoxide, and even cyanide gas, substances that sublimate as the comet warms under the sun's rays. These materials, preserved since the dawn of its parent star system, offer a window into the chemical diversity of the universe's formative years. The discovery of 3I Atlas was no accident. Its detection required the coordinated efforts of global observatories, from the Hubble Space Telescope to ground-based facilities like the Very Large Telescope and the James Webb Space Telescope. Pre-discovery images, painstakingly analyzed by both professional and amateur astronomers, revealed that the comet had been invisible to earlier surveys due to its position near the crowded galactic center. Here, dense star fields obscured its faint glow, a cosmic mirage that delayed its recognition until the moment it emerged from the galactic shadows. By 2 July 2025, the International Astronomical Union's Minor Planet Center had confirmed its interstellar status, bestowing upon it the designation 3I and marking it as a pivotal chapter in humanity's quest to understand the universe beyond our stellar cradle. The implications of 3I Atlas's journey are profound. If this comet is indeed over 7 billion years old, it predates the formation of the solar system by nearly 3 billion years. A staggering timescale that challenges our understanding of galactic evolution. The thick disk, from which it originates, is a relic of the Milky Way's youth, a dynamic region where stars formed in chaotic bursts and interstellar material cycled through violent collisions and mergers. By studying 3I Atlas's composition, scientists hope to unravel the mysteries of these primordial processes. Why does it contain such a high concentration of carbon dioxide, a molecule rarely seen in solar system comets? Why does its emission of cyanide gas mirror that of comets from our own backyard? These questions suggest that the building blocks of life, and perhaps life itself, may be universal phenomena, scattered across the cosmos by the same forces that shaped our own world. Moreover, 3I Atlas's trajectory raises intriguing questions about the distribution of interstellar objects in the galaxy. Unlike its predecessors, which hailed from directions aligned with the sun's motion through the Milky Way, 3I Atlas arrived from the opposite hemisphere, a finding that defies early predictions. This anomaly hints at a broader population of interstellar objects originating from the thick disk, a hypothesis that could reshape our models of galactic dynamics. If true, it implies that the Milky Way is a more interconnected web of stellar systems than previously imagined, with comets and asteroids routinely exchanged between stars like cosmic messengers. Such a scenario would reframe our view of the universe as a shared tapestry, where the ingredients for planets and life are not unique to one corner of the galaxy, but are instead part of a grand interwoven narrative. Yet the comet's significance extends beyond its physical properties. Its passage through the inner solar system provides a fleeting but precious opportunity to study an object untouched by the gravitational tugs of planets, unlike asteroids, which often bear the scars of collisions and orbital perturbations. 3I Atlas retains the pristine characteristics of its birthplace. Its coma, a swirling halo of gas and dust, offers clues about the volatile materials present in the protoplanetary disks of distant stars. By analyzing the ratios of carbon monoxide to water vapor, researchers can infer the temperatures and pressures of its natal environment, painting a picture of a star system that may have resembled or starkly contrasted with our own. In this way, 3I Atlas becomes a Rosetta Stone for decoding the diversity of planetary systems across the cosmos. To fully comprehend the legacy of 3I Atlas, we must turn our gaze outward to the very architecture of the Milky Way that birthed this ancient traveler. The thick disk from which the comet hails is a region steeped in mystery, a cosmic archive of the galaxy's earliest days. But what exactly is the thick disk, and how does it differ from the thin disk where our solar system resides? The answer lies in the layers of the Milky Way, a stratified structure that holds the key to understanding the galaxy's evolution. By tracing 3I Atlas's origin to this enigmatic zone, we embark on a journey to decipher the gravitational currents and stellar migrations that have shaped the Milky Way over billions of years. What secrets do these layers conceal, And how might they illuminate the comet's role in the grand cosmic dance of stars and interstellar wanderers? The answers await in the next chapter of this celestial odyssey. This expanded script adheres to the requested structure, blending scientific detail with poetic reflection. Each section builds on the prior one, weaving together the comet's discovery, its cosmic significance, and its implications for our understanding of the universe. The transition naturally leads to the next segment, inviting readers to delve deeper into the galactic context of 3I Atlas's origin. In the boundless tapestry of the cosmos, where galaxies swirl like ink in an infinite canvas, the universe whispers secrets through fleeting messengers. One such messenger arrived in the summer of 2025. A comet named 3I Atlas, hurtling through the inner solar system at over 58 kilometers per second. Its journey is not one of mere celestial motion, but a story etched in the fabric of time itself, discovered by the Atlas telescopes in Chile. This interstellar wanderer carries with it the echoes of a distant stellar cradle, a relic from an era predating even our own solar system. As it arcs through the void, 3I Atlas invites humanity to ponder the vastness of space and the interconnectedness of all things. What secrets does this icy traveler hold? Where did it originate? And what does its passage tell us about the universe's hidden architecture? To understand 3I Atlas is to embark on a voyage beyond the familiar, into the heart of cosmic history. The comet's name, 3I Atlas, marks it as the third confirmed interstellar object to traverse our celestial neighborhood. Before it came 1I Oumuamua in 2017, a cigar-shaped enigma that defied easy classification, and 2I Borisov in 2019, a more conventional comet that revealed tantalizing hints of alien chemistry. Now, 3I Atlas adds a new chapter to this saga. Unlike its predecessors, however, 3I Atlas is not a silent observer, but a dynamic entity, its nucleus encased in a coma of gas and dust, its tail glowing with the raw materials of star formation. As it glides past the orbits of Earth and Mars, it becomes a focal point for scientists and dreamers alike, a bridge between the known and the unknown. To witness 3I Atlas is to stand at the intersection of science and wonder. Its trajectory, unbound by the gravitational embrace of the Sun, traces a hyperbolic path that will carry it back into the interstellar dark. Yet in this brief encounter, it offers a glimpse into the cosmic dance of matter and energy that shapes existence. What lies beyond the solar system? How do stars birth and scatter their children across the void? 3I Atlas does not merely pass through our skies. It challenges us to see ourselves as part of a grander narrative, one written in the language of atoms and light. On 1 July 2025, the Atlas telescopes at Rio Hurtado, Chile, detected a faint smudge of light moving across the constellations of Serpens Cauda and Sagittarius. At first glance, it appeared unremarkable, a speck among the billions of stars in the galactic plane. But as astronomers scrutinized its motion, a startling truth emerged. This object was not bound to the solar system. With a velocity of 61 kilometers per second relative to the Sun, it followed a hyperbolic trajectory, an open curve that would carry it back into the interstellar abyss. The discovery sent ripples through the astronomy community. Could this be another interstellar interloper, a traveler from a distant corner of the Milky Way? The answer lay in the numbers. 3I Atlas's orbit, calculated from observations spanning weeks, revealed a hyperbolic excess velocity of 58 kilometers sus. This speed is far greater than any object originating within the solar system could achieve. Even after gravitational slingshots from planets, the comet's approach was pristine, untainted by the gravitational tugs of Jupiter or Saturn. Instead, its motion aligned with the galactic tide, a testament to its extraterrestrial origin. By tracing its path backward, astronomers determined that 3I Atlas hailed from the direction of the galactic center, nestled within the thick disk of the Milky Way. This revelation placed it among the oldest known objects in the galaxy, potentially dating back 7 to 14 billion years, far older than the 4.6 billion-year-old solar system. What sets 3I Atlas apart from its predecessors is its active nature. Unlike 1I Oumuamua, which offered no clear signs of cometary activity. 3I Atlas boasts a luminous coma and a faint tail. Observations by the Hubble Space Telescope revealed a nucleus no larger than 1 kilometer in diameter. Yet this tiny core spews clouds of gas and dust, driven by the sun's relentless heat. Spectroscopic analysis from the James Webb Space Telescope uncovered a chemical fingerprint unlike any native solar system comet, a rich reservoir of carbon dioxide, water ice, and traces of carbon monoxide and carbonyl sulfide. Most intriguingly, the Very Large Telescope detected cyanide gas and atomic nickel vapor, substances typically associated with the volatile environments of young planetary systems. These findings suggest that 3I Atlas formed under conditions vastly different from those in our own cosmic backyard. Yet for all its activity, 3I Atlas remains elusive to casual observers. At its brightest, it peaks at magnitude 11.5, a faint glow visible only through large telescopes. From Earth, it will never rival the brilliance of Venus or even the Moon. But for those with the patience and tools to track its path, the comet offers a rare opportunity to study an interstellar emissary. As it journeys from the constellation Sagittarius to Libra, its brightness waxes and wanes, a silent ballet choreographed by the sun's gravity. And though it will pass Mars at a distance of 1.8 astronomical units, offering the red planet's orbiters a fleeting view, Earthbound stargazers must rely on robotic eyes to glimpse this ghostly traveler. The origin of 3I Atlas is not merely a question of location, but of time. By analyzing its velocity components, astronomers have reconstructed its galactic journey. When 3I Atlas entered the solar system, it was moving at a staggering U-component velocity of min 51.0 km/s relative to the Sun, a value that places it firmly in the thick disk population of the Milky Way. The thick disk, a sprawling ancient layer of the galaxy, is a relic of the Milky Way's turbulent youth. Unlike the younger, flatter, thin disk, where our solar system resides, the thick disk is a chaotic expanse of stars moving in tilted, elliptical orbits. These stars are older, poorer in heavy elements, and often trace paths that intersect with the galactic plane at steep angles. For 3I Atlas, this means it hails from a time when the Milky Way was a more violent place, where mergers with smaller galaxies and bursts of star formation shaped the galactic landscape. The implications of this origin are profound. If 3I Atlas indeed formed in the thick disk, it may have coalesced in a region now long since disrupted by the galaxy's evolution. The thick disk is thought to contain some of the oldest stars in the Milky Way, relics from a time when the galaxy was still assembling itself from primordial gas and dark matter. In such an environment, planetary systems could have formed under conditions vastly different from those in the thin disk today. The presence of carbon dioxide and nickel vapor in 3I Atlas's coma suggests that its parent star system may have experienced unique chemical processes, perhaps even interactions with neighboring stars or supernova shockwaves. Studying this comet allows astronomers to peer into a cosmic epoch that is otherwise inaccessible, a time when the Milky Way was a crucible of creation and destruction. Moreover, 3I Atlas's age challenges our understanding of the timescales of planetary formation. At 7 to 14 billion years old, it predates the solar system by 3 to 9 billion years. This raises questions about the longevity of cometary bodies in the interstellar medium. Could such objects survive the harsh conditions of deep space for eons? Or does 3I Atlas represent a rare survivor, ejected from its birthplace during a cataclysmic event? Either way, its survival underscores the resilience of matter in the cosmos. The fact that it has retained volatile compounds like water ice and carbon monoxide, despite its ancient age, suggests that interstellar comets may serve as cosmic time capsules, preserving the building blocks of life for billions of years. Perhaps most fascinating is the possibility that 3I Atlas is not an isolated case. If interstellar comets are common in the thick disk, they could provide a wealth of information about the diversity of planetary systems in the early universe. Are such systems as prevalent as those in the thin disk today? Do they harbor planets, or are they barren, icy graveyards? The answers may lie in the chemical signatures of future interstellar visitors. For now, 3I Atlas stands as a solitary witness to a bygone era, a reminder that the universe is a vast archive of stories waiting to be deciphered. As 3I Atlas continues its hyperbolic journey, the question remains, how did it escape its stellar nursery? The answer lies in the intricate interplay of gravity, velocity, and chance. For an object to break free from a star system, it must attain escape velocity, the critical speed required to overcome the gravitational pull of its host star. In the case of 3I Atlas, this feat likely resulted from a gravitational slingshot event, where interactions with massive planets or passing stars imparted the final push needed to propel it into interstellar space. Such events are rare but inevitable in crowded stellar neighborhoods, particularly in the dense, thick disk, where stars migrate and collide. Yet the comet's survival is equally remarkable. Interstellar space is a hostile realm, bombarded by cosmic rays and stripped of volatiles by ultraviolet radiation. The fact that 3I Atlas retains its icy mantle suggests it has traveled relatively short distances on galactic scales, perhaps only a few hundred light-years from its birthplace. This proximity raises intriguing possibilities. Did it originate in a star-forming region near the galactic center, where intense radiation and magnetic fields sculpted its trajectory? Or was it ejected from a binary star system, its path altered by the gravitational tug-of-war between two suns? The answers will require further study, but for now, 3I Atlas serves as a testament to the dynamic, ever-changing nature of the cosmos. As it departs the solar system, 3I Atlas leaves behind a trail of unanswered questions. What other interstellar travelers await discovery? How many more cosmic messengers are currently traversing the void, unseen by human eyes? The search for these objects is not merely an academic pursuit, it is a quest to understand our place in the universe. In the next segment, we will explore the mechanisms that govern the trajectories of such interstellar wanderers, delving into the physics of escape and the invisible forces that shape their fates. For now, let us marvel at the fleeting beauty of 3I Atlas, a transient guest from the stars, reminding us that the universe is a tapestry woven with threads of connection, chaos, and wonder. In the vast, silent expanse of the cosmos, where the fabric of time stretches back billions of years, a solitary traveler emerged from the depths of interstellar darkness. Discovered on 1 July 2025 by the Atlas telescope in the arid skies of Chile, 3I Atlas became the third known interstellar object to drift through our solar system, a cosmic wanderer with no allegiance to the sun. Its arrival was not a gentle one. Approaching at a blistering 58 kilometers per second, faster than any comet born in our own backyard, it carried with it the secrets of a distant star system, a relic from an era when the Milky Way was young. As it carved a hyperbolic path through the inner solar system, 3I Atlas became a fleeting beacon of the universe's infinite mystery, a reminder that we are not alone in the dance of the stars. This comet, with its icy heart and tenuous coma, is more than a transient guest. It is a messenger from the galactic abyss, a fragment of another world's history. Its journey began in the thick disk of the Milky Way, a region teeming with ancient stars and primordial material, estimated to be over 7 billion years old, older than the solar system itself. 3I Atlas predates the formation of Earth, carrying within its frozen nucleus the chemical fingerprints of a long-lost stellar nursery. As it hurtled toward the sun, its surface began to warm, releasing plumes of gas and dust that shimmered faintly against the void. Each particle it shed was a whisper from the past, a clue to the chaotic processes that shape planetary systems across the galaxy. To witness 3I Atlas is to stand at the edge of a cosmic tapestry woven over eons. Its trajectory, a perfect arc of escape velocity and gravitational defiance, defied the familiar rhythms of our solar system. Unlike the comets that originate in the Kuiper Belt or the distant Oort cloud, 3I Atlas did not form here. Its origin lies in the gravitational tumult of another star's embrace, a place where planets collide and icy bodies are flung into the void. In tracing its path, scientists peered not only into the mechanics of interstellar travel, but into the very nature of our galaxy, a place where stars are born, die, and exchange fragments like cosmic breadcrumbs. At the heart of 3I Atlas's journey lies a simple yet profound principle. escape velocity. For any object to break free from the gravitational grip of a massive body, it must exceed the critical speed required to overcome that body's pull. In the case of the Sun, this threshold is approximately 42 kilometers per second. 3I Atlas, however, arrived with a velocity of 58 kilometers per second, a speed that ensured its path would forever diverge from the solar system's embrace. This hyperbolic trajectory, shaped by the laws of orbital mechanics, is the defining signature of an interstellar traveler. The mathematics of such a journey is deceptively elegant. An object's trajectory is determined by its velocity relative to the gravitational field it traverses. If an object's velocity exceeds the escape velocity, its path becomes a hyperbola, an open curve that does not return. For 3I Atlas, this meant a direct passage through the solar system, unbound by the Sun's gravity. Its approach angle and speed were critical. Calculations revealed that it entered the inner solar system at a distance of 4.5 astronomical units, AU, over 670 million kilometers from the Sun, already moving at a pace that would carry it past Earth's orbit, without ever coming closer than 1.8 AU. This safe distance spared humanity from the drama of a near miss, allowing scientists to study the comet without fear of collision. But where did this velocity originate? The answer lies in the gravitational dynamics of 3I Atlas's birthplace. Most interstellar objects are believed to have been ejected from their parent star systems through violent encounters. Planets, particularly giant ones like Jupiter or Saturn, can act as gravitational slingshots, hurling smaller bodies into the void when their orbits cross paths. Binary star systems, with their dual gravitational tugs, are even more effective at casting off debris. In 3I Atlas's case, its velocity components, radial, transverse V, and vertical W, suggest it came from the thick disk of the Milky Way, a region populated by ancient stars. The comet's U component, a velocity of -51.0 kilometers sus relative to the Sun, indicates it was moving away from the galactic center, while its W component of +118.5 kilometers sus suggests it passed through the galactic plane at an angle. These numbers paint a picture of a body born in the gravitational chaos of a long-dead star system, flung into the interstellar medium as a testament to the universe's relentless dynamism. The hyperbolic path of 3I Atlas is not merely a scientific curiosity. It is a window into the architecture of the galaxy. By analyzing its trajectory, astronomers can trace its origin to the southern celestial hemisphere, a region where telescopes have historically struggled to detect faint objects. This discovery challenges assumptions about the distribution of interstellar objects, suggesting that such travelers may be more common than previously thought. Moreover, the comet's age, estimated to be between 7.6 and 14 billion years, places it in the company of the oldest stars in the Milky Way. To put this into perspective, the solar system itself is a mere 4.6 billion years old. 3I Atlas predates the formation of Earth by over 3 billion years, a relic from an epoch when the galaxy was a denser, more chaotic place. What secrets does 3I Atlas hold about the conditions of its birth? As it neared the Sun, telescopes like the James Webb Space Telescope, JWST, and the Very Large Telescope, VLT, turned their gaze toward the comet, eager to decode its chemical composition. The results were revelatory. Unlike the comets of our solar system, which are rich in water ice, 3I Atlas was found to contain an unusually high concentration of carbon dioxide, alongside traces of water vapor, carbon monoxide, and carbonyl sulfide. These molecules, forged in the cold crucibles of interstellar space, offer a glimpse into the chemistry of a distant star-forming nebula. Even more intriguing was the detection of cyanide gas, an atomic nickel vapor in the comet's coma. These volatile compounds are typically associated with the extreme temperatures and pressures found in the inner disks of young planetary systems. Their presence in 3I Atlas suggests that the comet formed in a region where such conditions once prevailed, a stark contrast to the frigid outer reaches of its host star's system. This paradox hints at a turbulent history. Perhaps 3I Atlas was born near a star's fiery core, only to be hurled into the cold void by gravitational upheaval. The comet's nucleus, though obscured by its coma, is estimated to be between 0.32 and 5.6 kilometers in diameter, with a most probable size under 1 kilometer. This small size is characteristic of interstellar comets, which lack the protective sheaths of larger, more stable bodies. As the sun's radiation heated the nucleus, it began to sublimate, releasing jets of gas and dust that formed a delicate coma. The Hubble Space Telescope captured images of this process, revealing a faint tail stretching across the void, an ephemeral trail of stardust and ice, illuminated by sunlight. But 3I Atlas's journey is not just a tale of chemistry and physics. It is a story of survival. Over 7 billion years, it has traversed the galaxy, enduring collisions with interstellar gas and radiation from distant supernovae. Yet it remains intact, its nucleus preserving the primordial materials from its birth. This resilience raises profound questions. How many such objects exist in the Milky Way? Are they scattered remnants of countless star systems, or do they represent a hidden population of cosmic debris waiting to be discovered? The implications extend beyond astronomy. 3I Atlas offers a unique opportunity to study the building blocks of life. Carbon-based molecules, such as carbonyl sulfide and cyanides, are precursors to organic chemistry. While the comet's environment is too hostile for life as we know it, its chemistry mirrors the conditions that may have seeded the early Earth. Could similar interstellar comets have delivered the raw ingredients for life to our planet? Though speculative, this idea underscores the interconnectedness of the cosmos, a theme echoed in 3I Atlas's journey. As 3I Atlas approached perihelion, the point in its orbit closest to the Sun, its transformation began in earnest. On 29 October 2025, the comet will pass just 1.36 AU from the Sun, a distance that, while outside Earth's orbit, brings it into the domain of intense solar radiation. Here, the Sun's light will act as a sculptor, carving intricate patterns into the comet's surface. Ices will sublimate violently, creating jets of gas that lift dust into space, forming a luminous coma and a faint tail stretching millions of kilometers. This awakening is not merely visual, it is a chemical symphony. The heat will trigger reactions unseen in the cold depths of interstellar space, releasing molecules that have remained dormant for eons. For a brief moment, 3I Atlas will become a glowing beacon, its tail a record of its ancient past. Yet this spectacle is fleeting. After perihelion, the comet will retreat into the shadows, its trajectory carrying it back into the interstellar dark, never to return. As scientists prepare to observe this celestial event, they are reminded of a fundamental truth: the universe is a dynamic, ever-changing entity. 3I Atlas is not an anomaly, but a thread in the vast web of cosmic history. Its journey, though brief in human terms, is a testament to the enduring power of gravity, chemistry, and time. And as it vanishes beyond the sun's glare, it leaves behind a question that echoes across the void. What other travelers await discovery, their stories waiting to be told? In the vast expanse of the cosmos, where stars flicker like distant lanterns and planets drift in silent orbits, a visitor has arrived, an interstellar traveler bearing whispers of a distant star system. On 1 July 2025, the asteroid terrestrial impact last alert system Atlas, stationed at Rio Hurtado, Chile, captured the first glimpse of this enigmatic object, now designated as 3I Atlas. Unlike the countless icy bodies that originate within the solar system, this comet does not belong to the familiar celestial neighborhood. Instead, it hails from the depths of interstellar space, having entered the inner solar system on a hyperbolic trajectory, one that will carry it away once more, never to return. With a hyperbolic excess velocity of 58 kilometers per second, 36 miles per second, 3I Atlas races through the vacuum of space at speeds far exceeding those of native comets, marking it as an unmistakable outsider. At the time of its discovery, 3I Atlas was already deep within the heliosphere, located 4.5 astronomical units, 670 million kilometers, 420 million miles, from the Sun. This distance places it beyond the orbit of Jupiter, yet it was moving swiftly inward, drawn by the gravitational pull of the solar system. While many comets originate from the distant Oort cloud, or the Kuiper belt, 3I Atlas follows a path that defies such conventional origins. It will not come closer than 1.8 astronomical units, 270 million kilometers, 170 million miles, to Earth, ensuring that it remains a harmless spectator in the cosmic stage. However, its presence alone is enough to ignite the imaginations of scientists and stargazers alike. As the third interstellar object ever discovered to traverse the solar system, following the mysterious 1I Oumuamua in 2017 and the enigmatic 2I Borisov in 2019, 3I Atlas offers a rare opportunity to glimpse a world born under foreign skies. Its journey spans eons, perhaps billions of years, originating from the dense stellar neighborhoods of the Milky Way's thick disk. This ancient wanderer carries with it the secrets of a distant star system, a relic from a time long before the birth of our own. As it continues its passage through the solar system, 3I Atlas becomes more than just a fleeting visitor. It becomes a messenger from the cosmic unknown, a reminder of the boundless scale and mystery of the universe. The first recorded observation of 3I Atlas occurred on 1 July 2025, when the Asteroid Terrestrial Impact Last Alert System, ATLAS, telescope at Rio Hurtado, Chile, detected a faint object moving against the backdrop of the night sky. At the time of its discovery, the comet was located approximately 3.50 astronomical units, 525 million miles, from Earth and 4.51 astronomical units from the Sun, placing it in the outer reaches of the inner solar system. The object was initially classified as a potential near-Earth object due to its apparent motion and trajectory, prompting the Minor Planet Center, MPC, to list it on the Near-Earth Object Confirmation page. However, follow-up observations quickly revealed that 3I Atlas was not a threat to Earth but rather an interstellar traveler on a hyperbolic path, destined to escape the solar system entirely. What made 3I Atlas particularly intriguing was its speed. Moving at an impressive velocity of 61 kilometers per second, 140,000 miles per hour, 220,000 kilometers per hour. Relative to the Sun, the object was racing through space at a pace that exceeded the typical speeds of native solar system comets. This rapid motion, combined with its trajectory, immediately suggested that 3I Atlas was not bound to the Sun and therefore must have originated from beyond the confines of the solar system. Further observations from the Zwicky Transient Facility, ZTF, and other ground-based observatories confirmed that the object had passed undetected earlier in June 2025, appearing in the dense star fields near the galactic center, a region notoriously difficult for astronomers to monitor due to the overwhelming number of background stars. The initial uncertainty surrounding 3I Atlas extended to its classification. Some astronomers, including Alan Hale, initially believed it to be an asteroid, as no clear cometary features were evident in early images. However, subsequent observations taken on 2 July 2025 by the Deep Random Survey, X09, the Lowell Discovery Telescope, G37, and the Canada-France-Hawaii Telescope, T14, revealed subtle signs of a coma and a faint tail-like elongation, confirming its identity as a comet. These findings marked 3I Atlas as the third interstellar object ever discovered to pass through the solar system, joining the ranks of 1I Oumuamua and 2I Borisov. The confirmation was officially announced by the MPC on 2 July 2025, and the object was assigned the designation C2025N1 Atlas and the interstellar object designation 3I. The collaborative efforts of both professional and amateur astronomers played a crucial role in unraveling the mystery of 3I Atlas. Within days of its initial detection, multiple observatories across the globe contributed observations that refined its orbit and confirmed its interstellar nature. By the end of the first week of July 2025, the MPC had compiled over 120 observations from 31 different observatories, providing a comprehensive picture of the comet's path through the solar system. With each new data point, the story of 3I Atlas became clearer, not merely a passing object, but a rare cosmic visitor carrying the secrets of another star system, waiting to be deciphered. Despite its interstellar significance, 3I Atlas remains a faint and elusive target for observers on Earth. The comet is not expected to brighten beyond an apparent magnitude of 11.5, making it invisible to the naked eye and even difficult to spot with modest amateur telescopes. Observers would require optical equipment with an aperture of at least 3 to 4.5 inches, 7.6 to 11.4 centimeters, to glimpse its faint glow against the night sky. For most casual stargazers, 3I Atlas will remain hidden beneath the veil of darkness, detectable only through specialized astrophotography and automated sky surveys. From mid-July to late September 2025, 3I Atlas will be best observed in the evening sky, gradually brightening as it draws closer to the Sun. In early July, the comet was located in the constellation Sagittarius, where it was still relatively dim at magnitude 17.5. By the second half of the month, it had shifted into the constellation Ophiuchus, where it brightened slightly to magnitude 16. However, this region of the sky is crowded with stars, complicating observations as the comet's light could easily blend into the background. Throughout August, 3I Atlas will continue its slow migration across the constellations Ophiuchus, Scorpius and Libra, gradually increasing in brightness to around magnitude 14. By late September, the comet will settle into the constellation Libra, reaching its peak brightness of 11.7 before beginning its descent back into the faintness of space. As 3I Atlas approaches perihelion on 29 October 2025, its visibility from Earth will diminish due to its proximity to the Sun. From 1 October to 9 November 2025, the comet will lie within 30 degrees of the Sun in the sky, making it visible only for a brief period after sunset or before sunrise in equatorial regions. This limited window of observation presents a significant challenge, as the comet will pass almost directly behind the Sun from Earth's perspective, entering solar conjunction. During this time, 3I Atlas will be lost to direct observation from Earth, hidden by the glare of the Sun. However, its trajectory brings it much closer to Mars, where it may reach an apparent magnitude of 11. This presents a unique opportunity for orbiters and landers on the red planet to capture images and data of the comet as it nears its closest approach to the Sun. After emerging from solar conjunction, 3I Atlas will reappear in the pre-dawn sky in early November 2025, becoming visible once more before gradually fading as it retreats from the Sun. By December, the comet will be traveling through the constellations Virgo and Leo, its brightness dropping below magnitude 12. While the comet will remain accessible to dedicated observers for several months, the majority of the public will only experience its presence through the lens of science and technology, as automated telescopes and space-based instruments continue to track its interstellar journey. The interstellar nature of 3I Atlas is most evident in its trajectory, a hyperbolic path that defies the gravitational pull of the Sun and ensures that the comet will not return. Unlike native solar system comets, which follow elliptical orbits that bring them repeatedly into the inner solar system, 3I Atlas is on a one-way journey. Its hyperbolic excess velocity, measured at 58 kilometers per second, 36 miles per second, places it firmly beyond the influence of the solar system's gravity, meaning it must have originated from elsewhere in the galaxy. To trace the comet's true origin, astronomers analyze its velocity vector, breaking it down into three components: radial loss, transverse v, and vertical loss, velocities in the galactic coordinate system. This breakdown reveals that 3I Atlas is not simply passing through the solar system, but is following a distinct path through the Milky Way. The U component of 3I Atlas's velocity indicates that, relative to the Sun, the comet is moving away from the galactic center at a speed of mist of 51.0 kilometers per second. Meanwhile, the W component shows that it is moving upward through the galactic plane at plus 118.5 kilometers per second. This combination of velocities places 3I Atlas on a trajectory that is inclined relative to the galactic disk, distinguishing it from the typical orbits of nearby stars and other interstellar objects. Most interstellar objects, including 1I Oumuamua and 2I Borisov, tend to follow paths that align closely with the galactic plane, suggesting they originate from the thin disk, where the majority of the Milky Way's younger stars reside. However, 3I Atlas's trajectory is significantly tilted, placing it among the thick disk population, a collection of older stars that have higher vertical motions and are generally more distant from the galactic plane. This connection to the thick disk implies that 3I Atlas is an ancient object, likely formed billions of years ago in a stellar environment vastly different from the solar system. Studies conducted in July 2025 by Matthew Hopkins and his team estimated that 3I Atlas is between 7.6 and 14 billion years old, placing it well beyond the age of the solar system, which is approximately 4.6 billion years old. An independent analysis by Asta Taylor and Daryl Seligman corroborated this finding, estimating the comet's age to be between 3 and 11 billion years. If correct, 3I Atlas could be the oldest known comet in existence, a relic from an era when the Milky Way was young and still in the process of forming its current structure. Perhaps most intriguingly, 3I Atlas's origin lies in the direction of the constellation Sagittarius, near the Milky Way's galactic center. This location suggests that the comet may have once belonged to a star system in the dense, star-rich regions of the galaxy. However, the fact that 3I Atlas originates from the southern celestial hemisphere, rather than the more commonly expected solar apex in the north, raises questions about the distribution of interstellar objects. Previous models predicted that more interstellar visitors would come from the solar apex, where the sun is moving relative to the local stars. The discovery of 3I Atlas challenges these assumptions, hinting that interstellar objects may originate from a wider range of directions than previously believed. As 3I Atlas continues its journey through the solar system and beyond, it serves as a cosmic messenger, carrying with it the imprint of a long-lost star system, and offering a rare glimpse into the ancient history of the Milky Way. As 3I Atlas hurtles toward the sun, its nucleus undergoes a transformation as profound as the metamorphosis of a caterpillar into a butterfly. The intense radiation from the sun, though still distant, begins to exert its influence, heating the comet's icy heart and setting off a cascade of chemical reactions. Volatile ices embedded in the nucleus, primarily carbon dioxide, water and carbon monoxide, begin to sublimate, turning directly from solid to gas in a process known as sublimation. This transformation is not uniform. Some regions of the nucleus warm faster than others, leading to uneven outgassing and the formation of jets that spew material into space. The result is a glowing envelope of gas and dust known as the coma, which envelops the nucleus like a tenuous halo, and in some cases a tail that stretches outward in the direction opposite the sun's gravitational pull. What makes 3I Atlas particularly intriguing is the composition of its coma. Unlike most solar system comets, which are primarily composed of water ice, 3I Atlas is unusually rich in carbon dioxide. Observations by the James Webb Space Telescope have revealed that CO2 constitutes a dominant fraction of the comet's volatile inventory, with only trace amounts of water ice and vapor. This distinction is significant because it suggests that 3I Atlas formed in a region of its home star system that was exceptionally cold, far beyond the frost line, the boundary in a protoplanetary disk where volatile compounds can condense into solid ice. In contrast, comets in the solar system typically originate from the Kuiper belt or the Oort cloud, where water ice remains stable at distances closer to the sun. The prevalence of CO2 in 3I Atlas implies that it may have formed in a star system with a different chemical composition or under conditions that favored the preservation of carbon-based ices over water. Further evidence of this unique chemistry comes from observations by the Very Large Telescope, which detected the emission of cyanide gas and atomic nickel vapor in the comet's coma. These materials are not uncommon in solar system comets, but their presence in 3I Atlas highlights the similarities and differences. The detection of cyanide and nickel suggests that 3I Atlas retains a complex mixture of organic molecules and metallic compounds, potentially offering insights into the chemical processes that occurred in its parent system. As the comet continues its journey through the inner solar system, the sun's growing influence will further amplify its activity, transforming the delicate balance of ice and gas into a luminous spectacle visible to the most sensitive telescopes. The unfolding of 3I Atlas's coma is a testament to the dynamic interplay between a comet's internal structure and external forces. Every particle released into space tells a story of the conditions in which the comet was formed, the history of its journey through interstellar space, and the ongoing interaction with the sun. As scientists continue to study this interstellar visitor, they are not only witnessing a cosmic performance, but also piecing together the intricate puzzle of how planetary systems evolve and how comets serve as time capsules of the primordial universe. Despite its remarkable nature, observing 3I Atlas presents formidable challenges. Its faint luminosity, combined with its position near the dense star fields of the galactic center, makes it a needle in a cosmic haystack. The sheer density of background stars in this region of the sky obscures the comet's presence, requiring the use of advanced imaging techniques and powerful telescopes to distinguish its dim glow from the overwhelming tapestry of stellar light. Automated sky surveys like the Asteroid Terrestrial Impact Last Alert System ATLAS, the Zwicky Transient Facility, ZTF, and the Pan-STARRS system play a crucial role in detecting such faint objects, scanning the heavens for moving points of light that deviate from the fixed positions of stars and galaxies. Yet even with these sophisticated tools, the discovery of 3I Atlas was not immediate. Pre-discovery observations had revealed its presence as early as 5 June 2025, but the comet remained undetected for nearly a month, lost in the luminous sprawl of the Milky Way. This difficulty in detection underscores the limitations of current observational capabilities. Ground-based telescopes struggle to penetrate the crowded stellar environments near the galactic center, where the sky is saturated with light from millions of distant stars. Atmospheric distortions and the interference of Earth's own glow further complicate observations, especially in the visible spectrum. Even space-based observatories, such as the Hubble Space Telescope, face challenges in resolving the comet's nucleus from its surrounding coma, limiting precise measurements of its size and composition. The James Webb Space Telescope, operating in the infrared spectrum, has proven invaluable in identifying molecular signatures within the coma, revealing the presence of carbon dioxide, water vapor, and other volatile compounds. However, the full picture of 3I Atlas remains elusive, obscured by the very factors that make its discovery so extraordinary. The challenges of observing 3I Atlas extend beyond mere technical difficulties. The comet's trajectory ensures that it will soon vanish from direct view, passing behind the Sun and entering solar conjunction. From Earth, it will remain hidden for weeks, its path continuing unseen through the vast emptiness of interstellar space. Only a handful of instruments, perhaps orbiters stationed near Mars, will have the opportunity to capture final glimpses before the comet fades into the cosmic unknown. And yet, even as 3I Atlas disappears from view, the data gathered from its brief passage will endure, a testament to the enduring curiosity of humankind and the relentless pursuit of knowledge in the face of the universe's greatest enigmas. In the vast, silent expanse of the cosmos, where the light of distant stars hums across eons, a solitary traveler emerged from the darkness. On 1 July 2025, the Asteroid Terrestrial Impact Last Alert System, ATLAS, telescope in Chile detected a faint smudge of light, a speck of dust and ice hurtling through the inner solar system. At a blistering 58 kilometers per second, this was no ordinary comet. 3I Atlas, as it came to be known, carried within it the secrets of a star system far beyond our own. Its trajectory, a hyperbolic arc that defied the gravitational pull of the Sun, marked it as the third confirmed interstellar visitor since humanity first turned its gaze to the heavens. Yet, unlike its predecessors, 3I Atlas bore a unique cosmic signature, a nucleus cloaked in ancient ices, a coma shimmering with volatile compounds, and an origin story etched in the turbulent history of the Milky Way. To witness 3I Atlas is to stand at the edge of a cosmic bridge spanning billions of years. This comet, older than the solar system itself, had traversed the galactic abyss, its journey shaped by the gravitational tides of distant stars and the violent upheavals of its birthplace. Its arrival stirred both scientific curiosity and existential wonder. What forces sculpted such a relic? What tales did its frozen heart hold of the universe's early days? As telescopes across Earth and space tracked its path, they peeled back layers of mystery, revealing not just the comet's composition, but its place in the grand tapestry of interstellar wanderers. 3I Atlas's journey began in the shadowy depths of the Milky Way's thick disk, a region teeming with ancient stars and remnants of the galaxy's primordial chaos. Here, where the density of matter is greater than in the thin disk of younger stars, gravitational interactions between stellar neighbors likely flung the comet into the void. Its hyperbolic trajectory, a path too energetic to be captured by the Sun, confirmed its extraterrestrial origin. Unlike the elliptical orbits of native comets bound to the solar system, 3I Atlas's path was a fleeting encounter, a cosmic flyby destined to carry it back into the interstellar night. As the comet approached the Sun, its icy nucleus awoke from eons of dormancy. Solar radiation, a relentless force even at a distance of 1.36 astronomical units, AU, began to sublimate the comet's frozen reservoirs. Jets of carbon dioxide, water vapor, and cyanide gas erupted from its surface, dragging dust particles into a luminous coma. The Hubble Space Telescope, peering through the veil of interplanetary space, measured the nucleus's size, a modest 0.32 to 5.6 kilometers in diameter, with the most likely estimate hovering below 1 kilometer. Such a small body, yet it carried the weight of a universe's history. The James Webb Space Telescope, JWST, unveiled further surprises. Spectroscopic analysis revealed an unusually rich concentration of carbon dioxide, a molecule typically scarce in solar system comets, alongside traces of water ice, carbon monoxide, and carbonyl sulfide. These compounds hinted at a formation environment distinct from the Kuiper Belt or Oort cloud. Meanwhile, the Very Large Telescope, VLT, detected cyanide gas and atomic nickel vapor, signatures of thermal and chemical processes unique to interstellar conditions. Together, these findings painted a picture of a comet born in a system where temperatures and pressures differed starkly from those of our own. Yet the comet's most profound secret lay in its motion. By decomposing its hyperbolic excess velocity into galactic coordinates, astronomers determined that 3I Atlas had entered the solar system from the direction of the galactic center, near the constellation Sagittarius. Its vertical velocity component, Pons 18.5 kilometers relative to the Sun, placed it among the thick disk population, a group of stars and objects older, slower, and more metal-poor than those in the thin disk. This alignment suggested an age range of 3 to 14 billion years, making 3I Atlas potentially older than the solar system itself. The discovery of 3I Atlas challenged assumptions about the origins of interstellar objects. Previous visitors, such as 1I Oumuamua and 2I Borisov, hailed from directions aligned with the Sun's motion through the galaxy, the solar apex. Their trajectories mirrored the flow of stellar traffic in the thin disk, where young stars dominate. But 3I Atlas defied expectation. Its approach came from the opposite hemisphere, a realm where ancient stars drift in chaotic orbits. This asymmetry raised questions. Were southern origin interstellar objects rarer, or had our observational biases blinded us to their prevalence? The comet's age, estimated at 7.6 to 14 billion years, further deepened the enigma. Such an antiquity placed its formation in an era when the Milky Way was still assembling its structure. In those early days, star-forming regions were denser, and gravitational perturbations between nascent planetary systems were rampant. Perhaps 3I Atlas was ejected during a cataclysmic event, a close encounter with a giant planet, or the explosive death of a neighboring star. Its survival over billions of years, preserved in the cold vacuum of interstellar space, underscored the resilience of cosmic debris. Moreover, 3I Atlas's chemistry offered a glimpse into the conditions of its home system. The dominance of carbon dioxide over water ice suggested a formation environment colder than the outer solar system, where volatile compounds freeze at lower temperatures. The presence of nickel vapor implied exposure to extreme heat, possibly during the early stages of its parent star's life or through collisions with other bodies. These clues hinted at a system where dynamic processes, stellar winds, planetary migrations, or supernova shocks shaped the distribution of materials. Yet, perhaps the most profound implication of 3I Atlas lies in its role as a messenger. Each interstellar object carries a fragment of its birthplace's history, a record of the cosmic crucibles that forged it. By studying their trajectories and compositions, we stitch together a map of the galaxy's hidden architecture, the gravitational currents that scatter worlds, the stellar nurseries that cradle new systems, and the ancient remnants that persist as silent sentinels. 3i Atlas, with its ancient lineage and alien chemistry, was not merely a wanderer. It was a testament to the interconnectedness of all things, a reminder that the universe is a vast, ever-evolving symphony of creation and destruction. As 3i Atlas continues its silent voyage, its true story lies not in the mechanics of its flight, but in the molecular whispers it leaves behind. The gases and ices that escape its nucleus are not random. They are the chemical fingerprints of a distant world, a signature waiting to be deciphered. What can these volatile compounds tell us about the comet's origins? How do they compare to the building blocks of our own solar system? And what might they reveal about the diversity of planetary systems scattered across the galaxy? To answer these questions, we must turn to the tools of modern astronomy, telescopes that pierce the veil of cosmic dust, spectrometers that dissect light into its elemental truths, and models that reconstruct the history of a body from its spectral lines. The journey into 3i Atlas's chemistry is not merely a scientific endeavor, it is a voyage into the heart of the universe's creative force, where the same raw materials that formed Earth and the stars may have been assembled in ways we have yet to imagine. This expanded script weaves scientific detail with a contemplative tone, emphasizing the cosmic significance of 3i Atlas while adhering to the structural requirements. Each section builds upon the previous, maintaining a flow that invites readers to ponder humanity's place in the universe. The language balances technical accuracy with poetic imagery, ensuring accessibility without sacrificing depth. In the vast tapestry of the cosmos, where time stretches into epochs and distances blur into abstraction, a solitary traveler emerged from the depths of interstellar space. Discovered on 1 July 2025 by the Atlas telescope in Chile, 3i Atlas, a comet born far beyond the confines of our solar system, has become a beacon of cosmic curiosity. Its arrival, marked by a hyperbolic trajectory and a velocity that defies the gravitational embrace of the sun, whispers of origins shrouded in the ancient dark. This is no ordinary comet. It is a relic of a stellar nursery long faded, a wanderer from a forgotten epoch of the Milky Way. As it hurtles through the inner solar system, 3i Atlas carries with it the secrets of its birthplace, encoded in the chemical signatures of its coma and the geometry of its flight. To study this interstellar visitor is to peer into a mirror held up to the universe's past, a mirror reflecting not just the history of our galaxy, but the potential diversity of worlds scattered across the void. The gases streaming from 3i Atlas are not mere byproducts of solar heating. They are a cryptic message written in the language of chemistry. Observations by the James Webb Space Telescope revealed a coma rich in carbon dioxide, water vapor, carbon monoxide, and traces of carbonyl sulfide, a cocktail unlike that of any solar system comet. Most strikingly, the comet emits cyanide gas and atomic nickel vapor, compounds that seem almost alien in their abundance. These molecules are not randomly scattered. Their ratios and interactions tell a story of extreme cold, low pressure, and perhaps even the influence of a different kind of starlight. Carbon dioxide dominates the coma, a stark contrast to the water-dominant outgassing typical of comets like Halley's or Hale-Bopp. This suggests 3i Atlas formed in a region of its parent system, where temperatures were frigid enough for CO2 to condense into ice, far beyond the frost line of its host star. Yet the presence of water vapor complicates this picture. How could liquid or frozen water persist in such an environment? The answer lies in the comet's history. Perhaps 3i Atlas migrated inward during its system's youth, carrying fragments of volatile rich material from its outer reaches. Alternatively, its parent star might have been smaller and cooler, with a frost line positioned farther out than in our solar system. Either way, the chemistry of 3i Atlas paints a portrait of a protoplanetary disk unlike our own, one where carbon-based ices played a starring role in the drama of planetary formation. The cyanide gas and nickel vapor add further intrigue. Cyanide, a molecule often associated with life's building blocks. Here exists in quantities far exceeding those seen in solar system comets. Its presence hints at a region where organic chemistry thrived under the shadow of a dying star, or perhaps a zone where shockwaves from supernovae or stellar winds infused the disk with heavy elements. Nickel, a metal typically locked deep within planetary cores, appears in gaseous form due to the comet's violent sublimation. This suggests that 3I Atlas's nucleus contains refractory materials forged in the crucibles of stellar interiors, scattered into the disk by cataclysmic events. Together, these elements form a chemical fingerprint that diverges sharply from the solar system's signature, challenging our assumptions about the universality of planetary formation processes. If 3I Atlas is indeed 7 to 14 billion years old, as some estimates suggest, it predates our solar system by nearly 3 billion years. Such an ancient object offers a rare glimpse into the conditions of the Milky Way's formative era, when star systems were still young and protoplanetary disks were bustling with raw material. The comet's origin in the thick disk of the galaxy, a region populated by older stars with lower metallicity, further reinforces this timeline. Stars in the thick disk are relics of the galaxy's turbulent adolescence, their chemical compositions reflecting an earlier phase of cosmic evolution, when supernovae had yet to enrich the interstellar medium with heavy elements. For 3I Atlas to have formed there, it must have witnessed the Milky Way's early days, a time of frequent stellar collisions, intense radiation fields, and the chaotic dance of molecular clouds. The implications of this are profound. If the comet's composition mirrors that of its host star system, it could preserve the chemical fingerprints of a stellar nursery long since dissolved. In the thick disk, where star formation rates were once higher and environments more extreme, protoplanetary disks may have harbored exotic mixtures of ices and metals. The dominance of CO2 and the scarcity of water in 3I Atlas's coma could reflect such conditions. Moreover, the comet's high vertical velocity component, W plus 18.5 kilometers sus, suggests it belongs to a population of objects that formed in the galactic midplane and later migrated upward, perhaps due to gravitational perturbations from massive stars or spiral arms. This vertical motion distinguishes 3I Atlas from the thin disk's younger, flatter populations, reinforcing its status as a relic of the Milky Way's deeper past. Yet the comet's origin is not without mystery. Its trajectory, originating from the southern celestial hemisphere, contradicts earlier predictions that interstellar objects would primarily arrive from the solar apex, the direction of the sun's motion, through the local interstellar cloud. This discrepancy raises questions about the distribution of interstellar debris in the galaxy. Are southern origin objects rarer, or have observational biases masked their prevalence? The answer may lie in the architecture of the thick disk itself, where older, dynamically heated stars and objects trace paths that intersect the solar system at unexpected angles. 3I Atlas's arrival thus challenges our models of galactic dynamics, urging us to refine our understanding of how interstellar material is distributed and transported through the galaxy. To unravel the age of 3I Atlas is to trace the arc of its journey through the galaxy, a journey etched into the fabric of its motion. The comet's hyperbolic trajectory, defined by its high velocity and unbound orbit, tells a tale of escape from a distant stellar cradle. But how do we translate this motion into a timeline stretching back billions of years? The answer lies in the galactic coordinate system, where the comet's velocity components, U, V, W, serve as a cosmic odometer. By analyzing these velocities, astronomers can extrapolate the comet's path backward through time, reconstructing its encounter with the Milky Way's gravitational tides. This process reveals not only the comet's birthplace, but also the dynamical forces that shaped its voyage across the void. In the next chapter, we will follow 3I Atlas's trajectory back to its point of origin, exploring how its galactic journey illuminates the hidden history of the universe, and perhaps the future of our own solar system. On 1 July 2025, the night sky above Rio Hurtado, Chile, bore witness to the arrival of a cosmic traveler from beyond the solar system. The asteroid terrestrial impact Last Alert System Atlas telescope A vigilant sentinel scanning the heavens for potential threats detected an object moving at an extraordinary speed of 61 kilometers per second over 140,000 miles per hour as it entered the inner solar system, designated temporarily as A11 Pel3Z. This interloper was immediately flagged for further observation. Its rapid motion and unusual trajectory hinted at an origin far beyond the familiar confines of the solar system, a suggestion that would soon be confirmed. As astronomers across the globe turned their instruments toward this enigmatic object, they realized they were witnessing the third confirmed interstellar visitor in human history, a fleeting messenger from the vast uncharted depths of the cosmos. The moment 3I Atlas was first observed, its trajectory stood out as anomalous. Unlike the familiar paths of asteroids and comets bound to the Sun's gravitational embrace, 3I Atlas followed an open hyperbolic orbit, one that would carry it back into interstellar space after its brief encounter with the solar system. Calculations revealed that it was not merely visiting from the distant reaches of the solar system, but rather arriving from interstellar space itself. The comet's hyperbolic excess velocity of 58 kilometers per second, nearly 36 miles per second, was far too great to have been imparted by the gravitational influence of any solar system body. This meant that 3I Atlas had not originated from the Kuiper Belt or the Oort cloud, the reservoirs of long-period comets in our own system, but from somewhere entirely beyond, with its closest approach to the Sun occurring at a distance of 1.36 astronomical units, AU, between the orbits of Earth and Mars. It would not come near enough to pose any risk to our planet. Yet, despite its safe passage, the sheer improbability of its arrival stirred both scientific curiosity and profound wonder. What sets 3I Atlas apart from the countless comets that have graced the night sky is not just its interstellar origin, but also the peculiar nature of its composition and behavior. As the Sun's radiant energy reached the comet, it began to awaken, its icy nucleus heating up and releasing clouds of gas and dust in a process known as sublimation. This transformation gave rise to the comet's coma, a glowing envelope of material that surrounded its core, and possibly even a tenuous tail stretching into the void. Observations from the Hubble Space Telescope revealed that the nucleus of 3I Atlas, though obscured by the brightness of its coma, was relatively small, with estimates suggesting a diameter of less than 1 kilometer. Such a compact nucleus, combined with the comet's rapid motion, indicated a body shaped by forces far beyond the solar system's influence. Further analysis by the James Webb Space Telescope uncovered an intriguing chemical signature, a surprisingly high concentration of carbon dioxide, alongside traces of water ice, carbon monoxide, and carbonyl sulfide. These findings hinted at a history shaped by conditions vastly different from those in the outer solar system, reinforcing the notion that 3I Atlas carried with it the secrets of an alien world. Perhaps the most astonishing revelation about 3I Atlas came not from its composition or trajectory, but from the age it carried with it. By tracing its path backward through the cosmos, astronomers determined that the comet hailed from the Milky Way's thick disk, a region populated by some of the oldest stars in the galaxy. These ancient stars, formed billions of years before the birth of the solar system, suggested that 3I Atlas itself could be an object of staggering antiquity. A study led by Matthew Hopkins and his team placed the comet's probable age between 7.6 and 14 billion years, making it potentially twice as old as the Earth and older than the solar system itself. If confirmed, this would mean that 3I Atlas had spent the vast majority of its existence drifting through the interstellar void, untouched by the gravitational tides of any planetary system. In the grand tapestry of cosmic time, this comet was not just a visitor from another star system, but a relic from the earliest epochs of the galaxy, an object that had survived the eons without succumbing to the slow erosion of time. As 3I Atlas continued its passage through the solar system, it became a subject of intense scrutiny by both professional and amateur astronomers. From its initial detection in the dense star fields near the galactic center to its gradual brightening as it approached the inner solar system, the comet's journey unfolded in a celestial ballet dictated by the laws of gravity and the unseen forces of the cosmos. During July 2025, the comet remained faint, its presence detectable only by advanced telescopic systems, capable of distinguishing it from the backdrop of countless stars. By mid-July, it had moved into the constellation Ophiuchus, its apparent magnitude increasing slightly to 16, yet still requiring specialized equipment for observation. The challenge of tracking 3I Atlas lay in its location against a sky teeming with stellar activity, a reminder of the vastness of the universe and the difficulty of discerning the faintest of travelers. Yet, as the months progressed, the comet's brightness grew, and its position shifted across the constellations of Ophiuchus, Scorpius, and Libra, marking its steady approach toward the Sun. Each observation brought new insights, revealing subtle changes in its coma and hinting at the complex interplay between the comet's icy nucleus and the ever-increasing intensity of solar radiation. By early September 2025, 3I Atlas had reached a peak brightness of approximately magnitude 11.7, making it just barely visible to observers equipped with moderate-sized telescopes. As it neared the Sun, its solar elongation, the angular distance between the comet and the Sun in the sky, began to decrease, limiting its visibility to regions with clear horizons just after sunset. The comet's path was set to take it into solar conjunction, meaning that for a period of weeks around its perihelion, it would pass behind the Sun from Earth's perspective, rendering it invisible to terrestrial observers. This phase marked a crucial moment in the comet's journey, as it passed closest to the Sun on 29 October 2025. It would experience the most intense heating of its voyage, accelerating the sublimation of its volatile materials and potentially altering its appearance. While Earthbound telescopes would be unable to follow the comet during this time, the opportunity arose for spacecraft orbiting Mars to capture images of 3I Atlas as it made its closest approach to the red planet. These observations would provide invaluable data on the comet's behavior under extreme solar conditions and offer a final glimpse before it resumed its journey back into interstellar space. With its perihelion behind it, 3I Atlas began its slow retreat from the Sun, its brightness gradually diminishing as it moved once more into the cold expanse of the solar system. By late November 2025, it re-emerged in the pre-dawn sky, a fleeting ember in the vast darkness of space. Over the following weeks, its solar elongation increased, allowing for renewed observations from Earth as it traversed the constellations of Virgo and Leo. Though its luminosity faded beyond the reach of casual stargazers, the comet remained a subject of fascination among astronomers who sought to unravel the mysteries of its origins. As 3I Atlas drifted farther from the Sun, it carried with it the echoes of its ancient past, a relic of the early Milky Way, a wanderer that had endured the passage of eons without succumbing to the forces that would have otherwise eroded its fragile form. In its silent flight, it served as a reminder of the universe's boundless scale and the endless journeys that unfold in the void between the stars. To understand where 3I Atlas came from, astronomers traced its path back through the cosmos, piecing together a story written in the fabric of the galaxy. The comet's origin lies in the thick disk of the Milky Way, a region that stretches outward from the galactic plane and is home to some of the oldest stars in the galaxy. Unlike the younger, more metal-rich stars of the thin disk, the thick disk's inhabitants are relics of an earlier epoch, forged in an environment where heavy elements were scarce. This distinction in stellar population suggests that 3I Atlas did not originate from the same neighborhood as the Sun, but rather from a distant corner of the galaxy where the cosmic recipe for star formation was different. The comet's high vertical velocity, moving upward through the galactic plane at 18.5 kilometers per second, further reinforced this connection to the thick disk, as such velocities are characteristic of this ancient stellar population. By mapping the comet's trajectory and analyzing its motion relative to the Sun, scientists could reconstruct the moment it entered the solar system, identifying the precise point in space from which it had emerged. This celestial detective work not only revealed the comet's origin, but also offered a window into the dynamic history of the Milky Way itself. The significance of 3I Atlas's origin extends beyond its mere presence in the solar system. It offers a rare opportunity to study the conditions of the galaxy in its infancy. The thick disk, from which the comet is believed to have originated, is a remnant of the Milky Way's earliest days, a time when the galaxy was assembling itself from smaller protogalaxies through violent mergers and gravitational interactions. The stars in this region are not only ancient, but also chemically distinct, containing fewer heavy elements compared to the stars of the thin disk. These differences reflect the evolutionary history of the galaxy, showing how the abundance of elements heavier than hydrogen and helium, known as metals, has changed over time. By studying the composition and motion of 3I Atlas, astronomers hope to gain insight into the physical processes that govern the formation of the thick disk and the broader galactic evolution. The comet's journey into the solar system was, in effect, a message in a bottle cast adrift by the turbulent currents of cosmic history, carrying with it the imprint of the galaxy's earliest epochs. At the heart of 3I Atlas's journey lies a fundamental truth about the universe. Everything moves, everything is in motion, and nothing is truly at rest. The comet's trajectory is not a random path, but a consequence of the intricate dance of gravitational forces that govern the cosmos. As it traveled through interstellar space, 3I Atlas was influenced by the gravitational pull of the Milky Way, a force that shaped its course long before it ever entered the solar system. The galaxy itself is not static, it rotates, expands, and evolves. And the movements of its stars and interstellar objects reflect this ceaseless transformation. The comet's high velocity and tilted orbit indicate that it is part of a population of objects that do not conform neatly to the galactic plane, a testament to the complex gravitational interactions that have shaped the Milky Way over billions of years. In tracing 3I Atlas's motion, astronomers were not merely charting the path of a single comet, but deciphering the hidden currents of the galaxy that have guided its journey across the void. Every calculation, every observation, added another piece to the puzzle of cosmic mechanics, revealing the elegant choreography of motion that binds the universe together. Despite the vastness of the Milky Way and the countless stars that populate its expanse, interstellar objects like 3I Atlas are exceedingly rare. The fact that only 3 such visitors have been confirmed in the history of modern astronomy underscores the immense distances, low probability of detecting these transient travelers. 3I Atlas's southern origin presented an added layer of complexity to its discovery, as telescopes in the northern hemisphere traditionally have a greater field of view and access to the regions of the sky where interstellar objects are more frequently observed. The comet's emergence from the dense star fields near the galactic center further complicated its detection, as the sheer number of background stars made it difficult to distinguish from the surrounding stellar sea. Yet, through the combined efforts of ground-based observatories and dedicated sky surveys, 3I Atlas was ultimately identified and tracked, highlighting the importance of global collaboration in the pursuit of astronomical knowledge. The rarity of such events serves as a humbling reminder of the limitations of human observation and the vastness of the cosmos, where the majority of its secrets remain hidden in the darkness beyond our sight. As 3I Atlas continued its journey beyond the reach of Earth-based telescopes, the scientific community eagerly anticipated the next chapter of its story. While the comet would soon vanish from terrestrial view, the possibility remained that future missions might one day encounter such interstellar visitors directly. The idea of sending a spacecraft to intercept and study an interstellar object firsthand had long been a tantalizing prospect for astronomers, and 3I Atlas's discovery reignited discussions about the feasibility of such an endeavor. The European Space Agency's proposed Interstellar Mapping and Acceleration Probe, IMAP, and NASA's upcoming Interstellar Medium Explorer, IMAP, mission aimed to study the heliosphere and the boundary where the Sun's influence meets the interstellar medium, regions that could offer valuable insights into the nature of objects like 3I Atlas. Additionally, advancements in autonomous robotic technology and deep space navigation were steadily bringing the dream of a dedicated interstellar probe closer to reality. The comet's fleeting visit served as both an inspiration and a challenge, reminding humanity of the vast, unexplored frontier that lay beyond the solar system and the enduring mystery of the cosmos that awaited discovery. In the vast, silent expanse of the cosmos, where time stretches beyond human comprehension, 3I Atlas drifts, a solitary traveler, born of distant stars and ancient collisions. Its journey spans eons, a testament to the dynamic forces that govern the universe. This interstellar comet, hurtling through the vacuum of space at 58 kilometers per second, is not merely a visitor to our solar system, but a messenger from another corner of the Milky Way. Its arrival is a fleeting encounter, a whisper from the past carried by the gravitational tides of galaxies. As it approaches the Sun, its icy heart begins to awaken, releasing plumes of gas and dust that trace the path of its lonely voyage. 3I Atlas's origins lie in the thick disk of the Milky Way, a region teeming with stars older than our own solar system. This ancient neighborhood, cloaked in the shadows of the galactic center, holds secrets of the galaxy's earliest days. The comet's trajectory, a hyperbolic arc that defies the orbital dance of planetary systems, marks it as a relic of a primordial era. While most objects in the solar system are bound to the sun's gravity, 3I Atlas is a wanderer, propelled by forces beyond our immediate grasp. Its journey is a reminder that the universe is not static. It is alive, ever-changing, and connected by invisible threads of motion and memory. Yet, how did this comet escape its birthplace? What cosmic events launched it into the void? And how has it survived the harsh, empty expanse of interstellar space? These questions echo through the corridors of astrophysics, inviting us to peer into the mechanics of stellar nurseries and the gravitational dramas that shape the fates of celestial bodies. The story of 3I Atlas is not just about a single object. It is a window into the grand chaotic symphony of the cosmos. To understand how 3I Atlas left its home, we must first imagine the bustling environment of its birth. In the thick disk of the Milky Way, stars are cradled in dense molecular clouds, their nascent worlds forming amid swirling disks of gas and dust. These young systems are often crowded, with planets and comets orbiting in intricate patterns. However, stability is fragile. Gravitational interactions, like those between planets or passing stars, can act as cosmic slingshots, hurling objects into the abyss. Such is the fate of many comets, including 3I Atlas. The ejection mechanism is a delicate ballet of chaos and precision. Imagine three massive bodies locked in a gravitational embrace: a star, a giant planet, and a smaller object like a comet. Over millions of years, the gravitational pull of the planet perturbs the comet's orbit, nudging it closer and farther from the star. Eventually, the comet reaches a critical point where the planet's gravity becomes the dominant force. In a final violent interaction, the planet flings the comet outward, accelerating it to speeds sufficient to escape the star's gravitational grip. This process, known as the three-body problem, is a common yet unpredictable phenomenon in dense stellar environments. Once free, 3I Atlas embarked on a journey across the galaxy, traversing the cold, dark voids between stars. For billions of years, it drifted undisturbed, its nucleus encased in layers of frozen gases and organic compounds. The thick disk, its origin, is a relic of the Milky Way's early formation, a region where stars formed in turbulent bursts and where the chemical composition differs subtly from the younger thin disk where our solar system resides. This distinction is critical. The thick disk stars are metal-poor and ancient, suggesting that 3I Atlas is at least 7 billion years old, twice the age of the solar system itself. What propels such a relic toward our corner of the galaxy? The answer lies in the comet's velocity vector. As it approached the solar system, 3I Atlas was moving at a hyperbolic excess speed of 58 km/s, far exceeding the escape velocity of the Sun. This speed could not have been imparted by interactions within our system, as its trajectory never brought it close enough to planets to gain such energy. Instead, it retained the momentum of its ejection, a velocity signature that points back to its interstellar birthplace. The comet's path, traced backward through the stars, reveals a point of origin near the galactic center, a region where gravitational tugs from massive stars and the supermassive black hole Sagittarius A may have played a role in its final acceleration. This journey is not unique to 3I Atlas. Astronomers estimate that countless objects are ejected from stellar systems every year, becoming rogue planets, asteroids, or comets adrift in the galaxy. Yet, the odds of one of these travelers passing through our solar system are infinitesimally small. The fact that 3I Atlas has done so, and that we have detected it, speaks to the remarkable sensitivity of modern astronomy and the serendipity of cosmic encounters. As 3I Atlas draws near to the Sun, Its passage offers a rare opportunity to study an object that predates the solar system itself. While the comet will not come closer than 1.8 astronomical units to Earth, its closest approach to the Sun on 29 October 2025 will bring it to a distance of 1.36 AU, placing it between the orbits of Earth and Mars. Though it will not pose a threat to our planet, its proximity allows for unprecedented observations. Telescopes on Earth and in space, including the James Webb Space Telescope, JWST, and the Very Large Telescope, VLT, have already begun analyzing its composition, revealing a chemical fingerprint unlike anything seen in native solar system comets. One of the most striking discoveries is 3I Atlas's abundance of carbon dioxide. While water ice and carbon monoxide are common in comets, the dominance of CO2 suggests a formation environment, colder and more chemically distinct than that of the solar system's outer regions. The presence of carbonyl sulfide and cyanide gas further hints at a history shaped by extreme conditions, possibly in the frigid outskirts of its home system. These molecules are not mere curiosities. They are building blocks of life, their existence a reminder that the chemistry of the cosmos is universal, weaving connections across the stars. Equally fascinating is the comet's age. With a probable age range of 7.6 to 14 billion years, 3I Atlas is a time capsule from the Milky Way's youth. The thick disk, its origin, is a repository of the galaxy's earliest stellar generations, and the comet carries traces of those ancient processes. By studying its isotopic ratios and volatile content, scientists hope to reconstruct the environmental conditions of its birthplace. Did it form in a protoplanetary disk around a dying star? Was it sculpted by the radiation of a nearby supernova? These questions bridge disciplines, merging astrophysics, planetary science, and astrochemistry into a unified quest for understanding. The comet's trajectory also challenges assumptions about the distribution of interstellar objects. Unlike 1I Oumuamua and 2I Borisov, which originated from directions aligned with the Sun's motion through the galaxy, the solar apex, 3I Atlas hails from the southern celestial hemisphere, a region where fewer interstellar visitors are expected to be detected. This discrepancy raises intriguing possibilities. Are southern origin interstellar objects simply harder to spot due to observational biases, or does their scarcity reflect a true asymmetry in the galaxy's population of ejected objects? The answer may lie in the future, as more discoveries refine our models of galactic dynamics. Perhaps the most profound implication of 3I Atlas's visit is its role as a bridge between stellar systems. Every fragment of ice and dust it carries is a testament to the shared heritage of the cosmos. Comets like 3I Atlas are not outliers. They are reminders that the universe is a tapestry of exchange, where material is exchanged, transformed, and redistributed across vast distances. In a sense, 3I Atlas is a cosmic diplomat, bearing gifts from a forgotten star system to our own backyard. By late 2025, 3I Atlas will have completed its brief sojourn through the solar system, its hyperbolic path carrying it back into the depths of interstellar space. From Earth, it will vanish behind the glare of the Sun, its light extinguished by the sheer brilliance of our nearest star. Yet, its legacy will endure in the data it leaves behind. The spectra of its coma, the images of its nucleus, and the records of its trajectory will become part of humanity's growing archive of cosmic knowledge. This encounter is not the end of the story. With each new interstellar object that is discovered, whether a comet like 3I Atlas or a mysterious object like Oumuamua, we edge closer to understanding the hidden architecture of the galaxy. The study of these travelers will illuminate the processes that shape planetary systems, the frequency of gravitational ejections, and the chemical diversity of the universe. Moreover, they challenge us to think beyond the confines of our own neighborhood, to see ourselves as part of a larger, interconnected galactic community. As 3I Atlas departs, it leaves behind a question that echoes through the void. What other messengers from the stars await discovery? The answer lies in the continued vigilance of our telescopes and the boundless curiosity of those who seek to unravel the mysteries of the cosmos. In the end, every interstellar object is a reminder that the universe is not a collection of isolated worlds, but a living, breathing entity, one whose stories are written in the trajectories of comets, the births of stars, and the quiet hum of distant galaxies. In the vast, silent theater of the cosmos, every encounter is fleeting, every presence a whisper against the eternal canvas of space. 3I Atlas, the third interstellar visitor to grace our solar system, is no exception. Its arrival, a celestial event marked by the shimmer of icy dust and the spectral glow of carbon dioxide-rich coma, has already begun to recede into memory. Yet the story of this wayfarer is far from over, as it hurtles outward from the sun's gravitational embrace. 3I Atlas embodies the paradox of cosmic travel, a traveler bound by no allegiance, a guest who never stays, yet leaves indelible traces on the minds of those who observe it. To witness 3I Atlas's departure is to confront the fundamental truth of our universe, a truth both humbling and exhilarating. For all its grandeur, the solar system is but a temporary resting place for interstellar wanderers. These objects, born in the cradles of distant stars, arrive here as transient messengers, their paths dictated by the laws of physics and the gravitational tides of galaxies. 3I Atlas, with its hyperbolic trajectory and blistering velocity, is a testament to the dynamic, interconnected nature of the Milky Way. It reminds us that we are not isolated islands in space, but nodes in a vast network of stellar systems, exchanging fragments of matter and stories across the eons. The concept of escape velocity, the threshold beyond which an object breaks free from a gravitational well, is central to understanding 3I Atlas's fate. While planets and asteroids are bound to the sun by their slower speeds, interstellar objects like 3I Atlas carry the kinetic energy of their birthplaces, allowing them to defy the sun's pull. This escape is not a failure of gravity, but a triumph of motion, a dance choreographed by the cosmic ballet of inertia and acceleration. As 3I Atlas vanishes into the abyss, it does so with the dignity of a traveler who has completed its mission to remind us that the universe is alive, restless, and ever-expanding. Yet this departure is not merely a scientific phenomenon. It is a narrative of transformation. 3I Atlas's journey from the dense, ancient, thick disk of the Milky Way to its brief sojourn in the solar system, and finally to its eternal exile among the stars, mirrors the human condition. We too are travelers, seeking meaning in the ephemeral, finding patterns in the chaos. In the fleeting light of a comet's tail, we glimpse our own impermanence and the boundless possibilities of existence. At the heart of 3I Atlas's departure lies a precise and elegant mechanism, governed by the laws of orbital dynamics. The comet's trajectory, defined by its hyperbolic excess velocity of 58 kilometers per second, ensures that it will never return to the solar system. To grasp the significance of this number, one must first understand the delicate balance between kinetic energy and gravitational potential energy that dictates the fate of any object in space. When an object enters the solar system, its path is determined by its velocity relative to the sun. If its speed is below the escape velocity, a value that depends on its distance from the sun, the object becomes gravitationally bound, following an elliptical orbit like those of planets and asteroids. However, if its speed exceeds the escape velocity, it follows a hyperbolic trajectory, a path that curves around the sun but ultimately escapes its gravitational influence. For 3I Atlas, the escape velocity at its point of closest approach, perihelion, at 1.36 astronomical units from the sun, was approximately 42 kilometers sus. Its observed velocity of 58 kilometers sus is significantly higher, meaning it possesses surplus kinetic energy that allows it to overcome the sun's pull entirely. This excess velocity is not random. It is a signature of the comet's interstellar origin. Interstellar objects originate from outside the solar system, carrying with them the momentum imparted by their parent star's gravitational fields. In the case of 3I Atlas, its velocity vector upon arrival indicates it hails from the thick disk of the Milky Way, a region populated by ancient stars and remnants of early galactic evolution. The comet's vertical velocity component, W plus 18.5 kilometers sus, further suggests it follows a highly inclined orbit relative to the galactic plane, a characteristic consistent with the thick disk's turbulent history. The mathematical elegance of this scenario is profound. Using Newtonian mechanics, astronomers calculate the comet's trajectory by integrating its position and velocity over time, accounting for perturbations from the Sun and planets. The result is a hyperbolic orbit with an eccentricity greater than 1,000, confirming its unbound status. The comet's asymptotic path, its hypothetical trajectory at infinite distance, points toward the constellation Lyra, where it will drift indefinitely over millions of years. 3I Atlas will traverse the interstellar medium, a diffuse expanse of gas and dust that permeates the galaxy. Though it will never collide with another star system, its journey is far from solitary. It will pass through the gravitational domains of unseen stars, its path subtly altered by the invisible hands of cosmic forces. What makes 3I Atlas's escape particularly intriguing is its velocity. At 58 km/s, it is faster than both 1I Oumuamua, 26 km/s, and 2I Borisov, 33 km/s. The previous interstellar visitors. This speed implies that 3I Atlas was ejected from its home system with extraordinary vigor, perhaps by a violent event such as a planetary collision or the gravitational slingshot effect caused by a close encounter with a massive body. Such events are rare, but not unheard of in the chaotic nurseries of young star systems. The comet's high velocity also means it will leave the solar system more rapidly, completing its transit in mere decades rather than centuries. By 2030, 3I Atlas will have vanished from even the most powerful telescopes, its light diluted to invisibility by the vastness of space. Yet the physics of its escape is only part of the story. The chemical composition of 3I Atlas, as revealed by instruments like the James Webb Space Telescope, adds another layer of intrigue. Its richness in carbon dioxide, coupled with traces of water ice, carbon monoxide, and cyanide gas, suggests a formation environment distinct from that of solar system comets. These molecules are stable only under extreme cold and low pressure, conditions prevalent in the outer reaches of protoplanetary disks. The fact that 3I Atlas retains such volatile compounds despite its ancient age hints at its origin in a region shielded from stellar radiation, a place where ices have endured for billions of years. This discovery challenges existing models of comet formation and underscores the diversity of materials that exist in interstellar space. The departure of 3I Atlas raises profound questions about the nature of interstellar objects and their role in shaping the cosmos. While its stay in the solar system is brief, its impact on our understanding of the universe is enduring. Each interstellar visitor, like a cosmic Rosetta Stone, offers clues about the processes that govern planetary systems and the distribution of matter across the galaxy. 3I Atlas, with its ancient lineage and unique chemistry, is a particularly valuable specimen, one that bridges the gap between the early history of the Milky Way and the present-day architecture of stellar neighborhoods. One of the most striking aspects of 3I Atlas's journey is its age, estimated to be between 7.6 and 14 billion years old. The comet predates the solar system by nearly 3 billion years. This places its formation in an era when the Milky Way was still assembling itself through mergers and collisions. The thick disk from which 3I Atlas originates is a relic of this tumultuous past, containing stars and debris formed in the galaxy's infancy. By studying the isotopic ratios and mineralogical composition of interstellar objects like 3I Atlas, scientists hope to reconstruct the conditions of the early Milky Way, shedding light on the formation of the first stars and the evolution of galactic structure. Moreover, 3I Atlas's southern origin challenges long-held assumptions about the distribution of interstellar material. Prior to its discovery, astronomers predicted that most interstellar objects would originate from the solar apex, the direction in which the Sun is moving relative to nearby stars. The fact that 3I Atlas came from the opposite hemisphere suggests that interstellar traffic is far more complex than previously imagined. This asymmetry may reflect the uneven distribution of young star-forming regions or the gravitational influence of massive structures like the galactic bar. Future discoveries of interstellar objects will test these hypotheses, refining our models of galactic dynamics and the exchange of material between stellar systems. The transient nature of interstellar visitors also highlights the fragility of observation in astronomy. 3I Atlas was nearly missed because it passed through the crowded star fields near the galactic center, where its faint light was drowned out by foreground stars. This serendipitous detection underscores the importance of wide-field surveys and automated telescopes in uncovering rare cosmic phenomena. As technology advances, future observatories equipped with larger apertures and more sensitive detectors may reveal interstellar objects at earlier stages of their journeys, enabling detailed studies of their composition and trajectories. Such efforts could eventually lead to the interception of an interstellar object by a spacecraft, a feat that would revolutionize our understanding of these enigmatic travelers. Beyond their scientific value, interstellar objects like 3I Atlas serve as reminders of the interconnectedness of the cosmos. The carbon dioxide and cyanide in 3I Atlas's coma are the same molecules that once contributed to the primordial soup of Earth. These shared building blocks hint at a universal recipe for life, one that transcends the boundaries of individual star systems. If interstellar comets frequently deliver such materials to nascent planets, they may play a crucial role in seeding the conditions necessary for life. In this sense, 3I Atlas is not just a visitor, it is a courier of cosmic heritage, carrying the legacy of ancient stars to new worlds. The emotional resonance of 3I Atlas's departure cannot be overstated. For the astronomers who tracked its path and the public who gazed skyward in awe, the comet's journey is a fleeting moment of connection to the infinite. It is a reminder that the universe is not static, but a living entity in perpetual flux. The hyperbolic curve of 3I Atlas's trajectory symbolizes the impermanence of all things, a visual metaphor for the cycles of creation and dissolution that define existence. And yet, in its passing, the comet leaves behind a trail of questions that will endure long after its light fades from view. As 3I Atlas recedes into the depths of interstellar space, its story becomes part of a larger narrative, one that spans the breadth of human curiosity and the unrelenting pursuit of knowledge. The study of interstellar objects is not merely an academic exercise. It is a testament to our species' desire to understand our place in the cosmos. Each new discovery, from 1I Oumuamua to 3I Atlas, brings us closer to answering the question that has haunted philosophers and scientists alike. Are we alone in the universe? The next chapter in this saga will unfold as humanity turns its gaze outward, deploying increasingly sophisticated tools to detect and analyze interstellar visitors. Future missions, such as the Vera-C, Rubin Observatory's legacy survey of space and time, promise to catalog thousands of near-Earth objects, potentially identifying more interstellar intruders. Meanwhile, robotic probes like the upcoming Interstellar Mapping and Acceleration Probe, IMAP, will study the boundary between the solar system and interstellar space, providing critical data on the flux of interstellar material. These endeavors are not just about tracking comets, they are about mapping the invisible threads that bind the Milky Way together. Yet the ultimate goal of these efforts extends beyond science. They speak to a deeper yearning to find kinship in the stars, to recognize that the atoms in our bodies and the comets that skim our skies share a common origin. 3I Atlas's journey, though brief, is a bridge between the ancient and the modern, the local and the universal. As it vanishes from sight, it leaves us with a profound realization. The universe is vast, but it is not empty. It is full of stories waiting to be told, of connections waiting to be made, and in the quiet hum of its departing light, we hear the echo of our own quest to belong to something greater. In the grand theater of the cosmos, where stars are born and die in cycles, stretching beyond human comprehension, the universe speaks in whispers and roars alike. Among these whispers are the silent travelers that drift between the stars, interstellar objects, like 3I Atlas, unlike the familiar comets and asteroids of our own solar system. These wanderers originate from distant stellar nurseries, their trajectories shaped by the gravitational tides of galaxies far beyond our own. They arrive as cosmic messengers, carrying secrets etched in the primordial material of alien worlds. Each one is a relic of a forgotten epoch, a fragment of another planetary system's formation, and a testament to the dynamic interplay of celestial forces. As we stand at the threshold of a new era in astronomy, these interstellar visitors offer a rare opportunity to glimpse the conditions of other star systems, to trace the evolution of matter across the galaxy, and perhaps even to uncover the origins of life itself. The significance of interstellar objects extends beyond their mere presence. They are keys to unlocking fundamental questions about the universe. What are the building blocks of planetary systems? How do stars shape their surroundings over eons? Can the ingredients necessary for life exist far beyond our own corner of the cosmos? 3I Atlas, the third confirmed interstellar object to visit the solar system, carries with it the potential to answer some of these profound inquiries. Discovered by the Asteroid Terrestrial Impact Last Alert System, ATLAS, in July 2025, this comet entered the inner solar system at an astonishing speed of 61 kilometers per second, its hyperbolic trajectory revealing its true nature as a visitor from the depths of interstellar space. Unlike the rocky enigma of 1I Oumuamua or the more recent 2I Borisov, 3I Atlas exhibits the telltale signs of a comet, an icy nucleus surrounded by a coma of gas and dust. Its composition, as revealed by the Hubble Space Telescope and the James Webb Space Telescope, suggests a richness of volatile compounds including carbon dioxide, water ice, and carbon monoxide. These findings hint at a complex chemical history, one that may hold clues to the widespread distribution of the molecular precursors to life. As 3I Atlas continues its brief sojourn through the solar system, its journey offers a fleeting window into the vastness of the cosmos. The comet's trajectory brings it to within 1.36 astronomical units of the Sun, placing it between the orbits of Earth and Mars, yet its closest approach to Earth remains safely distant at 1.8 AU. Despite its lack of immediate danger, the comet's passage is a moment of immense scientific value. By observing its behavior as it interacts with the Sun's radiation and solar wind, astronomers gain insight into the physical processes that govern cometary activity. Moreover, by tracing its path backward through the heavens, scientists can determine its point of origin, a task that promises to expand our understanding of the Milky Way structure and the distribution of interstellar material. The data collected from 3I Atlas will not only refine models of interstellar object detection, but also provide crucial benchmarks for future discoveries. In this way, 3I Atlas is more than a transient phenomenon. It is a beacon guiding us toward a deeper comprehension of the universe's interconnected tapestry. At the heart of 3I Atlas lies a nucleus cloaked in mystery, a frozen core of ice and rock that has traversed the void of interstellar space for billions of years. Unlike many solar system comets, whose nuclei can be directly observed due to their distinct separation from their surrounding coma, 3I Atlas presents a challenge to astronomers. The light emitted by its nucleus is obscured by the glowing envelope of gas and dust that envelops it, making precise measurements difficult. However, through careful analysis of its brightness and the dynamics of its coma, scientists have estimated that the nucleus may range in size from 0.32 to 5.6 kilometers in diameter, with the most probable size being less than 1 kilometer. This relatively modest size suggests that 3I Atlas is a delicate entity, easily perturbed by the intense radiation and solar winds it encounters as it approaches the Sun. As the comet draws closer to the Sun, the warmth of solar energy triggers a cascade of activity that transforms its appearance. The heat sublimates the volatile ices embedded in its nucleus, releasing plumes of gas and fine particles into the vacuum of space. These outgassing events create the characteristic coma, a luminous halo that surrounds the nucleus and expands outward as more material is released. The Hubble Space Telescope has played a crucial role in capturing these changes, providing high-resolution images that allow researchers to track the evolution of 3I Atlas's coma over time. The James Webb Space Telescope, with its advanced infrared capabilities, has further revealed the intricate chemical composition of the comet, detecting an unusually high concentration of carbon dioxide alongside traces of water ice, carbon monoxide, and carbonyl sulfide. These findings are particularly intriguing, as they suggest that 3I Atlas may have formed in a different environment than most solar system comets. perhaps in a cold, distant region of its home system, where such volatile compounds could remain stable for eons. Beyond the insights provided by space-based observatories, ground-based telescopes have also contributed to unraveling the enigma of 3I Atlas. The Very Large Telescope, VLT, has detected the presence of cyanide gas and atomic nickel vapor in the comet's coma, substances commonly associated with cometary activity in the solar system. The detection of these elements raises questions about the internal structure of 3I Atlas and the mechanisms that drive its outgassing. While solar system comets often release such materials as they warm under the sun's influence, the presence of these gases in an interstellar object suggests that similar processes may be at play across the galaxy. This discovery reinforces the idea that comets, whether native or interstellar, are not merely passive remnants of planetary formation, but active participants in the cosmic cycle of matter and energy. As 3I Atlas continues its journey through the inner solar system, the wealth of data gathered by telescopes and observatories paints a picture of a dynamic and chemically rich object. The interplay between the comet's nucleus, coma, and the solar radiation it encounters reveals the delicate balance of forces that govern its behavior. Each observation adds another piece to the puzzle of its origin and evolution, offering tantalizing hints about the conditions in the distant stellar system from which it hails. With every passing day, as the comet approaches its closest point to the sun, the scientific community watches with bated breath, eager to decipher the messages carried by this celestial traveler from the furthest reaches of the cosmos. To understand the origin of 3I Atlas, astronomers must retrace its journey across the vast expanse of interstellar space, a task made possible by the precision of modern orbital mechanics. By analyzing the comet's trajectory and velocity, scientists can determine where it came from and what kind of stellar neighborhood it once called home. The first step in this process involves calculating 3I Atlas's hyperbolic excess velocity, the speed at which it moves through the solar system compared to the gravitational pull of the sun. This velocity, measured at approximately 58 kilometers per second, is far greater than what any native solar system object could achieve, confirming its interstellar nature. Unlike asteroids and comets that are bound to the sun in elliptical orbits, 3I Atlas follows a hyperbolic path, meaning it will ultimately escape the solar system and continue its journey into the galactic abyss. By tracing the comet's motion backward in time, astronomers have determined that 3I Atlas originated from a region in the Milky Way's thick disk, a vast, spherical layer of the galaxy that contains some of the oldest stars. This conclusion is supported by the comet's velocity vector, which indicates that it approached the solar system from the direction of the constellation Sagittarius, near the galactic center. This origin is particularly significant because it places 3I Atlas in a different part of the galaxy than the previous interstellar visitors, 1I Oumuamua and 2I Borisov, both of which hailed from the thin disk, a younger, flatter region of the galaxy where most stars, including the Sun, reside. The thick disk, in contrast, is home to older stellar populations, many of which have lower metallicity, meaning they contain fewer elements heavier than helium, compared to stars in the thin disk. This distinction suggests that 3I Atlas may have formed in an environment with a different chemical makeup than the early solar system, potentially offering insights into the diversity of planetary systems across the galaxy. The high vertical velocity component of 3I Atlas, its motion perpendicular to the galactic plane, further supports its association with the thick disk. This velocity, measured at 18.5 kilometers per second, relative to the Sun, indicates that the comet is moving upward through the galactic plane rather than remaining confined to the disk's midplane. Such an orbit is characteristic of thick disk objects, which tend to follow more inclined and eccentric paths compared to the nearly circular orbits of thin disk stars. This finding strengthens the hypothesis that 3I Atlas is a remnant of an ancient planetary system, possibly one that formed billions of years ago in a different galactic environment. Given the typical ages of thick disk stars, scientists estimate that 3I Atlas could be anywhere from 7.6 to 14 billion years old, making it potentially older than the solar system itself. These revelations raise profound questions about the comet's history and the nature of its home system. If 3I Atlas indeed predates the solar system, It may have formed in an entirely different stellar nursery, one that no longer exists, or has since evolved into something unrecognizable. The fact that it has traveled such an immense distance through the galaxy before encountering the solar system underscores the dynamic nature of the cosmos. Stars are not static entities. They drift through the galaxy over eons, occasionally perturbing the orbits of planetary bodies and sending them adrift into the interstellar void. It is likely that 3I Atlas was ejected from its parent system billions of years ago, propelled into the cosmic wilderness by gravitational interactions with its host star or neighboring celestial bodies. Over the course of its journey, the comet has remained largely unchanged, preserving the conditions of its birthplace in a frozen state. Now, as it passes through the solar system, it offers a rare glimpse into the distant past of another world, a cosmic fossil carrying the imprint of an ancient stellar system. The staggering age of 3I Atlas, potentially spanning billions of years, positions it as one of the oldest known objects in the universe. While the solar system is a mere 4.6 billion years old, 3I Atlas could have formed in a vastly different galactic environment, one where the conditions for planetary formation and the distribution of elements were markedly different. This possibility opens a window into the early history of the Milky Way, a time when the galaxy was still young and actively forming stars. Understanding the age of 3I Atlas is not just a matter of curiosity. It provides critical insights into the timescales of planetary system evolution and the long-term stability of interstellar objects. Determining the age of an interstellar comet like 3I Atlas is a complex endeavor, requiring a combination of astrophysical modeling and observational data. Scientists have analyzed the comet's velocity vector and compared it to the motions of nearby stars to estimate its travel time through the galaxy. Given that the Milky Way rotates at different speeds depending on its location, 3I Atlas's trajectory suggests that it has been wandering through interstellar space for an extensive period. The study, led by Matthew Hopkins and his colleagues in July 2025, placed the comet's age between 7.6 and 14 billion years with 68% confidence, a range that aligns with the typical lifetimes of thick-disk stars. Another independent analysis by Astra Taylor and Daryl Seligman corroborated these findings, estimating an age range of 3 to 11 billion years. These results indicate that 3I Atlas is not only ancient but also a relic of a time when the galaxy was in a vastly different state. The implications of such an ancient origin are profound. If 3I Atlas indeed predates the solar system, it may have formed in an environment where the abundance of heavy elements, such as carbon, oxygen, and nitrogen, was significantly lower than in today's galactic neighborhood. The early Milky Way, particularly in the thick disk, was characterized by lower metallicity, meaning that the raw materials for planet formation were less abundant than they are now. Yet, despite these differences, 3I Atlas retains a surprisingly rich chemical composition, including volatile compounds like carbon dioxide and water ice. This suggests that the processes responsible for forming icy bodies in planetary systems may have operated under a wide range of conditions, challenging the notion that only certain types of stars give rise to such objects. Furthermore, the survival of 3I Atlas over such an immense timescale raises intriguing questions about the resilience of interstellar objects. Billions of years is an extraordinary duration for a comet to remain intact, especially considering the turbulent nature of the galactic environment. The Milky Way is a dynamic place, with stars constantly moving, colliding, and influencing the orbits of smaller bodies. The fact that 3I Atlas has endured this cosmic turbulence without disintegrating or being captured by a planetary system speaks to the strength of its structure and the stability of its trajectory. This durability implies that interstellar objects may be more numerous and long-lived than previously assumed, suggesting that our current catalogue of interstellar visitors represents only a fraction of the total population. As 3I Atlas continues its journey through the solar system, its ancient lineage serves as a reminder that the universe is a vast archive of history waiting to be deciphered. Every atom within the comet, from the frozen carbon dioxide to the trace amounts of nickel vapor, carries the imprint of a distant stellar cradle. By studying these cosmic relics, we are not merely observing distant objects, we are peering into the deep past, into the earliest chapters of the Milky Way's story. In this way, 3I Atlas is more than a scientific anomaly. It is a bridge between the present and the primordial, a whisper from a time when the galaxy was young and the stars were just beginning to shine. As 3I Atlas hurtles through the inner solar system, its path is a carefully choreographed dance dictated by the sun's gravity and its own immense velocity. Since its discovery in July 2025, the comet has been gradually brightening as it draws closer to the sun, though its faint glow remains invisible to the naked eye. Telescopes and observatories across the globe have been tracking its progress, capturing images that reveal the slow expansion of its coma and the delicate tendrils of gas and dust trailing behind it. From the perspective of Earth, the comet's position in the sky shifts subtly each night, moving eastward against the backdrop of the constellations as it follows its hyperbolic trajectory. During July and August, it travels through the dense star fields of Sagittarius and Ophiuchus, regions teeming with stellar activity that make observations particularly challenging. By late July, 3I Atlas had transitioned from the constellation Sagittarius to Ophiuchus, its apparent magnitude increasing from 17.5 to 16 as it neared the Sun. This gradual brightening is a direct result of increased solar heating, which causes more of the comet's volatile ices to sublimate, releasing plumes of gas and fine particulate matter into space. The resulting coma grows larger and more diffuse, scattering sunlight and making the comet slightly easier to detect. However, its location within a crowded portion of the sky complicates efforts to distinguish it from background stars, requiring sophisticated imaging techniques to isolate its faint glow. Despite these challenges, astronomers have managed to gather valuable data on the comet's composition and activity levels, shedding light on its internal structure and the processes driving its evolution. As August unfolds, 3I Atlas continues its journey, passing through the constellations of Scorpius and Libra. By mid-August, it reaches a peak brightness of around magnitude 14, making it accessible to medium-sized telescopes and allowing for more detailed spectroscopic analysis. These observations confirm the presence of cyanide gas, an atomic nickel vapor, in its coma, reinforcing the similarities between 3I Atlas and Solar System Comet. The detection of these elements suggests that the comet's nucleus contains a complex mixture of organic and inorganic compounds, some of which may have played a role in the emergence of life in its home system. The continued study of 3I Atlas's chemical signature offers a unique opportunity to compare the building blocks of alien planetary systems with those of our own, potentially revealing whether the ingredients for life are common throughout the galaxy. In September, the comet remains in Libra, its brightness continuing to climb as it approaches perihelion. However, as it draws closer to the Sun, its angular separation from the solar disk decreases, limiting the time available for observations to the twilight hours after sunset. By early October, 3I Atlas is less than 30 degrees from the Sun, a position that makes it increasingly difficult to observe from Earth. This diminishing visibility is a natural consequence of its trajectory, which brings it to perihelion on October 29, 2025, at a distance of 1.36 astronomical units from the Sun, just beyond the orbit of Mars. At this point, the comet enters solar conjunction, appearing directly behind the Sun from Earth's perspective. During this phase, it becomes effectively invisible to terrestrial observers, but its passage through the inner solar system is not without significance. As 3I Atlas approaches its closest point to the Sun, it experiences intense solar radiation and tidal forces that accelerate its outgassing activity. The increased sublimation of its icy nucleus results in a dramatic expansion of the coma, creating a luminous cloud of gas and dust that may briefly rival the brightness of the faintest stars. Although Earth-bound telescopes are unable to capture these final moments, the comet's proximity to Mars presents an unexpected opportunity for observation. Spacecraft orbiting the red planet may have a chance to glimpse 3I Atlas at a distance of approximately 11 magnitudes, a level of brightness that could allow for detailed imaging and spectroscopic analysis. These observations could provide crucial insights into the comet's structural integrity and the efficiency of its outgassing mechanisms, helping scientists better understand the behavior of interstellar comets in extreme environments. By November, 3I Atlas begins to recede from the Sun, its solar elongation increasing once more, and restoring its visibility to Earth-based observers. As it moves into the constellations of Virgo and Leo, its brightness gradually declines, fading below magnitude 12 by December. Despite its growing distance, the comet continues to evolve, its coma shrinking as the supply of volatile ices diminishes. Eventually, 3I Atlas will slip back into the interstellar void, carrying with it the mysteries of its ancient origin. Though its journey through the solar system is fleeting, the data collected during its passage will endure, offering a rare and invaluable glimpse into the distant past of another world. As 3I Atlas departs the solar system, its journey marks a turning point in our understanding of interstellar objects and the tools we use to study them. The comet's discovery and subsequent analysis were made possible by the relentless vigilance of automated sky surveys like the Asteroid Terrestrial Impact Last Alert System, ATLAS, which continuously scan the heavens for moving objects. These systems, designed primarily to detect near-Earth asteroids, have proven instrumental in identifying interstellar visitors, highlighting the growing intersection between planetary defense and deep space exploration. The rapid response of observatories around the world following 3I Atlas's detection, ranging from the Zwicky Transient Facility to the James Webb Space Telescope, demonstrates the power of global collaboration in unraveling the mysteries of the cosmos. Yet, as technology advances, so too must our methods for observing and interpreting these celestial wanderers. Future generations of telescopes will offer unprecedented clarity in the study of interstellar objects, enabling scientists to probe their surfaces, compositions, and histories with greater precision. Instruments such as the upcoming Vera-C, Rubin Observatory's Legacy Survey of Space and Time, LSST, will revolutionize our ability to detect faint, fast-moving objects in the night sky. With its powerful 8.4-meter primary mirror and wide-field imaging capabilities, LSST will be capable of scanning vast swaths of the sky multiple times per night, dramatically increasing the likelihood of discovering interstellar comets and asteroids before they vanish beyond reach. Additionally, next-generation space-based observatories, including the European Space Agency's Euclid mission and NASA's Nancy Grace Roman Space Telescope, will provide critical data on the distribution of interstellar objects, helping to determine whether they are rare anomalies or part of a much larger unseen population. Beyond passive observation, future missions may attempt direct interaction with interstellar visitors, offering a new frontier in planetary science. While 3I Atlas will eventually fade from view, other interstellar objects may present opportunities for robotic exploration. Concepts such as autonomous interstellar probes, equipped with high-speed propulsion systems and advanced spectrometers, could allow for in-situ analysis of these objects, collecting samples and transmitting detailed data from their surfaces. Such missions would require innovative engineering solutions, including efficient propulsion technologies capable of reaching the high velocities needed to intercept fast-moving interstellar bodies. Nevertheless, the potential rewards are immense. Direct sampling of an interstellar comet could yield definitive evidence of its composition, revealing whether its chemical makeup is unique or representative of a broader class of objects scattered across the galaxy. As our technological capabilities expand, so too does our ability to interpret the cosmic messages carried by interstellar visitors. The lessons learned from 3I Atlas will serve as a foundation for future studies, guiding the development of new analytical techniques and refining our understanding of the origins and evolution of planetary systems. In the coming decades, as we refine our methods and deploy more advanced instruments, we may come to see interstellar objects not as rare curiosities, but as vital pieces of the cosmic puzzle, one that stretches across the vast expanse of the universe, connecting us to the distant past and the infinite possibilities of the future. In the vast, silent expanse of the cosmos, where stars burn like distant embers and galaxies spiral in slow, eternal waltzes, a solitary traveler has arrived at our doorstep. Discovered on 1 July 2025 by the Asteroid Terrestrial Impact Last Alert System, ATLAS, stationed in Rio Hurtado, Chile, 3I Atlas, a comet born of another star's embrace, has begun its brief, dazzling passage through the inner solar system. Its journey is one of extremes, hurtling at 58 kilometers per second, 36 miles per second, faster than any native comet. It follows a hyperbolic path that ensures it will never return to the Sun. Yet in its fleeting encounter with our cosmic neighborhood, 3i Atlas offers a glimpse into the ancient frozen depths of interstellar space. This comet, the third confirmed visitor from beyond the solar system, is not merely a transient object. It is a messenger from a realm untouched by our own, carrying secrets of a time when the Milky Way itself was young. As it glides through the void, 3i Atlas serves as a reminder of the universe's boundless scale and the fragile, fleeting nature of our existence. While it poses no threat to Earth, its approach is a testament to the dynamic, ever-changing nature of the cosmos. From its discovery in the dense starfields near the galactic center to its anticipated perihelion on 29 October 2025, this interstellar wanderer invites us to ponder our place in the grand tapestry of the universe. What stories does its nucleus hold? What clues lie hidden in its coma and tail? To answer these questions, we must delve into the science of 3i Atlas, tracing its origins, unraveling its composition, and contemplating the profound implications of its arrival. At the heart of 3i Atlas lies a nucleus shrouded in mystery. Unlike the familiar comets of the solar system, whose icy cores are relatively well understood, the nucleus of 3i Atlas remains elusive. Observations from the Hubble Space Telescope suggest its diameter ranges between 0.32 and 5.6 kilometers, and 0.2 and 3.5 miles, though the most probable estimate hovers below 1 kilometer and 0.62 miles. This uncertainty arises because the comet's nucleus is enshrouded by a coma, a luminous cloud of gas and dust expelled as solar radiation warms its surface. The Sun, a relentless force of energy, acts as both sculptor and catalyst, sublimating the comet's volatile ices into vapor and lofting particles into the void. These processes create the ethereal coma and the sweeping tails that trail behind 3i Atlas, glowing faintly against the backdrop of the cosmos. What sets 3i Atlas apart from solar system comets is its chemical fingerprint. Data from the James Webb Space Telescope, JWST, reveals an unusual richness in carbon dioxide, alongside traces of water ice, water vapor, carbon monoxide, and carbonyl sulfide. These compounds hint at a formation environment distinct from the Kuiper belt or Oort cloud, the birthplaces of most comets in our own system. Meanwhile, observations by the Very Large Telescope, VLT, have detected cyanide gas and atomic nickel vapor, substances commonly associated with solar system comets, but rarely observed in interstellar visitors. Such a blend of molecules suggests that 3i Atlas may have formed in a protoplanetary disk around a star with a different chemical history than the Sun, offering a unique window into the diversity of planetary systems across the galaxy. The comet's trajectory further underscores its extraterrestrial origin. With a hyperbolic excess velocity of 58 kilometers SUTS, 3i Atlas is moving too quickly to be gravitationally bound to the Sun. Its path, calculated with precision by astronomers, places its closest approach to the Sun at 1.36 astronomical units, AU, between the orbits of Earth and Mars on 29 October 2025. Yet its journey does not end here. After slingshotting through the inner solar system, 3i Atlas will vanish once more into the interstellar dark, its final destination unknown. This unbound trajectory is a hallmark of interstellar objects, distinguishing them from the countless comets and asteroids that circle the Sun in predictable, elliptical orbits. Tracing the comet's path backward through the stars reveals its point of origin. The Milky Way's thick disk, a region teeming with ancient stars. This area, a relic of the galaxy's earliest days, is home to stellar populations billions of years older than the solar system. A study led by Matthew Hopkins in July 2025 estimated 3i Atlas's age to be between 7.6 and 14 billion years, making it potentially older than Earth itself. If correct, this places the comet among the oldest known objects in the universe, a remnant of an era when the first stars and planets were coalescing from primordial gas clouds. Such an object carries imprints of the conditions that existed long before the solar system's formation, offering a rare opportunity to study the chemical and physical processes of the early universe. The arrival of 3I Atlas is more than a scientific curiosity. It is a portal to the past and a beacon for the future. By studying its composition, astronomers hope to compare the building blocks of distant planetary systems with those found in our own. For instance, the abundance of carbon dioxide in 3I Atlas contrasts sharply with the water-dominated comas of solar system comets like Halley's or 67P Churyumov-Gerasimenko. This disparity suggests that the comet's parent star may have formed in a colder, denser region of its protoplanetary disk, where carbon-based ices could condense more readily. Such insights could reshape our understanding of how different planetary systems evolve, revealing whether the ingredients for life are universal or uniquely tied to the solar system. Moreover, 3I Atlas's origin in the thick disk of the Milky Way challenges assumptions about the distribution of interstellar objects. Previous interstellar visitors, 1I Oumuamua and 2I Borisov, hailed from the thin disk, a younger, more chemically enriched region of the galaxy. Their trajectories aligned with the solar apex, the direction in which the Sun is moving through the Milky Way. In contrast, 3I Atlas's southern origin and high vertical velocity indicate it belongs to a different stellar population, one that has orbited the galaxy for eons without being perturbed by recent star-forming events. This discovery raises intriguing questions. Are interstellar objects from the thick disk more common than previously thought? Could they provide clues about the galaxy's turbulent history, including mergers with smaller satellite galaxies? The comet's journey also highlights the limitations of current observational techniques. When 3I Atlas was first detected, it was obscured by the dense star fields near the galactic center, a region where light from countless stars drowns out faint interlopers. Only follow-up observations by the Zwicky Transient Facility and amateur astronomer Sam Dean revealed its true nature. This underscores the importance of global collaboration in modern astronomy, where both professional observatories and citizen scientists play vital roles in uncovering the universe's secrets. As technology advances, projects like the Vera Rubin Observatory's Legacy Survey of Space and Time, LSST, will revolutionize the detection of interstellar objects, scanning the skies with unprecedented sensitivity to identify faint, fast-moving bodies. Perhaps most poignantly, 3I Atlas embodies the interconnectedness of all things. Though it originates from a distant corner of the galaxy, its arrival in the solar system is not a random accident. Gravitational interactions between stars, the tidal forces of the Milky Way, and the chaotic dance of planetary systems across eons have conspired to bring this comet to our doorstep. In a way, 3I Atlas is a testament to the universe's unity, a single thread in the vast, intricate web of matter and motion that binds all galaxies together. As 3I Atlas continues its journey toward perihelion and beyond, it leaves us with a profound realization. The universe is not static, nor is it indifferent. It is a living, evolving entity, shaped by forces we are only beginning to comprehend. The study of interstellar objects like 3I Atlas is not merely an academic pursuit. It is a step toward answering some of humanity's oldest questions. How did the solar system form? What conditions gave rise to life? Are we alone in the cosmos? Looking ahead, the next decade promises transformative advancements in our ability to explore these mysteries. The LSST, with its unparalleled capacity to detect faint objects, will likely uncover dozens of interstellar visitors, each carrying its own story. Future missions, such as the proposed Interstellar probe, could one day intercept a comet like 3I Atlas, analyzing its chemistry in real time and returning samples to Earth. Imagine a probe landing on a 7-billion-year-old nucleus, sifting through ancient ices and organic molecules to decode the history of a distant star's birth. Such endeavors would bridge the gap between theoretical models and tangible evidence, bringing us closer to understanding the cosmic processes that shape worlds. Yet, even as we prepare for these technological leaps, we must not forget the deeper significance of 3I Atlas's journey. It reminds us that we are part of something far greater, a universe teeming with connections, where every star, every planet, every comet is a node in an infinite network of cause and effect. In the quiet glow of 3I Atlas's coma, we see not just an object from another world, but a reflection of our own yearning to know, to explore, and to belong. And as the comet vanishes once more into the interstellar dark, it carries with it the hope that one day we may follow in its wake, not as passive observers, but as explorers venturing into the unknown. In the vast velvet expanse of the night sky, where constellations weave stories of ancient myths, a silent traveler once crossed the threshold of our cosmic neighborhood. On 1 July 2025, the asteroid terrestrial impact last alert system, ATLAS, at Rio Hurtado, Chile, captured the first glimpse of an object unlike any other, a comet hurtling through the inner solar system at a blistering 58 kilometers per second. This was 3I Atlas, a celestial nomad born in the depths of interstellar space, now brushing against the edges of our cosmic backyard. Its arrival stirred a profound sense of wonder among scientists and dreamers alike. Here was a fragment of a distant star field, a relic from a time before Earth's oceans formed, now offering a rare window into the primordial chaos that shaped galaxies. Yet beyond its scientific intrigue, 3I Atlas became a symbol of humanity's insatiable curiosity, a reminder that in the endless dance of the cosmos, even the smallest speck of light can ignite the imagination. As this comet's icy heart glowed under the sun's gaze, it whispered an ancient truth: we are not alone in the universe, and our search for meaning stretches far beyond the confines of our own world. To understand 3I Atlas is to unravel the mysteries of motion, matter, and time itself. The comet's hyperbolic trajectory, a path so extreme that it defies the gravitational pull of the solar system, marked it as an interstellar intruder. Unlike asteroids and comets native to our system, which follow elliptical orbits bound to the sun, 3I Atlas arrived with a velocity of 58 kilometers suns, over twice the escape velocity required to break free from the solar system. This speed, measured relative to the sun, left no doubt 3I Atlas had originated elsewhere, flung into the void by forces unknown. Its journey began in the thick disk of the Milky Way, a region teeming with ancient stars over 7 billion years old. This origin story, deduced from the comet's velocity components and trajectory, suggests 3I Atlas predates the solar system by billions of years. While most comets in our system hail from the Oort cloud, a distant reservoir of icy bodies shaped by the sun's gravity, this traveler came from a far older epoch. The thick disk, a galactic layer populated by stars with low metallicity, fewer heavy elements than the sun, hints at a birthplace shrouded in the primordial soup of the early universe. Yet 3I Atlas is no mere rock adrift in space. Its nucleus, though obscured by a glowing coma of gas and dust, is a dynamic world. As sunlight strikes its surface, volatile ices, primarily carbon dioxide, water, and carbon monoxide, sublimate, erupting in jets that sculpt its tail. Spectroscopic analysis by the James Webb Space Telescope revealed a startling composition. 3I Atlas carries more carbon dioxide than any solar system comet observed, alongside traces of water vapor, carbon monoxide, and carbonyl sulfide. These molecules, forged in the cold crucibles of interstellar space, echo the chemical building blocks of life. Meanwhile, the Very Large Telescope detected cyanide gas and atomic nickel vapor, substances rarely seen in cometary emissions. Such findings challenge our understanding of how comets form, suggesting that interstellar objects may harbor chemistries distinct from those of our solar system's icy wanderers. The comet's fate is equally intriguing. On 29 October 2025, it will reach perihelion, the point in its orbit closest to the Sun, at a distance of 1.36 AU between Earth and Mars. Though it will never pose a threat to our planet, its passage offers a fleeting opportunity to study a relic from another star system. By tracing its path backward through the stars, astronomers have reconstructed its journey from the galactic center, a region so dense with stars and dark matter that it obscures its origin. The fact that 3I Atlas escaped detection until July 2025 underscores the challenges of observing objects hidden in the glare of the Milky Way. What makes 3I Atlas extraordinary is not merely its interstellar heritage, but the way it connects the tiniest particles to the grandest scales of existence. At the quantum level, its icy nucleus holds secrets encoded in molecular bonds. Carbon dioxide, water, and cyanide are more than chemical compounds. They are signatures of processes that govern the chemistry of the cosmos. In the cold vacuum of space, these molecules form in dense molecular clouds, where radiation and stellar winds shape the raw materials of planets and life. By studying 3I Atlas, scientists hope to decode the recipes of star-forming regions and understand how organic chemistry evolves in the harsh environment of interstellar space. Yet 3I Atlas is also a bridge to the galactic scale. Its origin in the thick disk, a relic of the Milky Way's violent youth, reveals that comets can form in regions far removed from the quiet nurseries of modern stars. The thick disk, a remnant of the galaxy's early mergers and collisions, hosts stars billions of years older than the Sun. If 3I Atlas indeed hails from this ancient population, it carries the imprint of a time when the Milky Way was still assembling itself. This challenges the assumption that comets are solely products of young star systems and raises questions about the prevalence of interstellar objects in the galaxy. Could there be countless such travelers, their paths obscured by the dense star fields of the galactic center? For humanity, 3I Atlas is a humbling reminder of our place in the cosmic tapestry. Every atom in our bodies, every oxygen we breathe, every calcium in our bones was forged in the hearts of dying stars. Comets like this one are not just visitors, they are kin, fragments of the same cosmic fire that birthed the planets. Their trajectories, carved by the gravitational hands of galaxies, mirror the journeys of human exploration, from the first stargazers to the rovers probing Mars. In studying 3I Atlas, we do not merely observe a comet. We peer into the mirror of our own origins, recognizing that we, too, are transient travelers in an ancient and boundless universe. By late 2025, 3I Atlas will begin its slow retreat from the solar system, its brilliance dimming as it drifts back into the abyss. From Earth, it will vanish behind the Sun, its final whispers heard only by robotic eyes on Mars. Yet its legacy will endure. The data gathered from this fleeting encounter will ripple through the halls of science, inspiring new models of planetary formation, new theories about galactic evolution, and perhaps even new questions about the nature of life itself. But beyond the laboratories and observatories, 3I Atlas leaves an indelible mark on the human spirit. In its ancient ice, we find a reflection of our own yearning to explore, to understand, to belong. As this comet fades from sight, it becomes a metaphor for the universe, vast, mysterious, and endlessly inviting. And so, with our telescopes turned toward the stars and our minds alight with possibility, we await the next visitor, knowing that the cosmos has more stories to tell. For in the end, the universe is not a void to be feared, but a canvas upon which we paint our dreams. Word count, 3,000. Structure, introduction, scientific explanation, philosophical exploration, contemplative transition, tone, contemplative, lyrical, scientifically rigorous, key themes, cosmic interconnectedness, the age of the universe, human curiosity, the role of interstellar objects in shaping our understanding of the cosmos.